Hello there. I'm so glad you found your way here tonight. Right now, as you settle in, something extraordinary lies hidden beneath the fabric of existence. A place smaller than atoms, smaller than protons, where the building blocks of the universe may not be particles at all. It is a theory that suggests beneath everything we see lies an invisible symphony of tiny vibrating strings. These strings are thought to be so small that if an atom were the size of the solar system, a string would still be invisible. Their vibrations could decide whether something appears as an electron, a photon, or even the force of gravity itself. And in order for the mathematics to work, the universe may need hidden dimensions, entire directions of space curled up beyond our sight. Tonight, we journey into the quiet and elegant world of string theory. We will explore over 100 soothing facts about this bold framework, from vibrating strings that give rise to every particle to hidden dimensions folded into the fabric of reality, from the unification of all forces to the possibility of multiple universes. There is no test at the end, no rush, no urgency, just the gentle unfolding of one of the most ambitious ideas in physics to carry you softly towards sleep. So let your breathing slow, let your thoughts grow quiet, and imagine those tiny strings humming gently in the darkness, weaving the universe with their hidden music. Welcome to Drowsy Discovery. I am glad you found your way here tonight. Perhaps you have had a long day. Perhaps you simply enjoy falling asleep to thoughts about the remarkable structures hidden at the foundation of reality. Either way, this space is for you. There is something deeply calming about contemplating the hidden world of vibrating strings. Every particle, every force, every flicker of light may carry within it a story far deeper than we ever imagined. You are part of that story. The same strings that may shape electrons and quarks are woven through your very being. The mathematics of the cosmos, if string theory is true, resonates in every atom of your body. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too, one sleepy soul at a time. But for now, all you need to do is relax. So settle in, let the weight of the day drift away, and let us begin with the first of many quiet truths about string theory. String theory is patient beyond measure. Its mathematics has been developing for decades. Its predictions may take generations to test, and yet, within all that patience, there are sudden bursts of wonder, ideas that connect gravity with quantum mechanics, dualities that link seemingly different theories, visions of reality that stretch beyond anything we can directly observe. Tonight, we will wander through this magnificent theoretical landscape. We will meet the strings that may underlie all matter. We will discover the hidden dimensions that give the theory its power. And we will uncover truths about string theory that may surprise even the most curious minds. But there is no hurry. String theory has been developing since the 1960s. It can continue its quiet evolution while you rest. Let us begin with what string theory truly proposes. String theory proposes that particles are not fundamental, but emerge from vibrating strings. At the heart of string theory lies a beautifully simple idea. The fundamental building blocks of the universe are not point-like particles, as most of 20th century physics assumed, but tiny, one-dimensional filaments of energy that vibrate at different frequencies. Just as a violin string produces different musical notes depending on how it vibrates, these fundamental strings produce different particles depending on their pattern of vibration. An electron is not a featureless dot, but a string vibrating in one particular mode. A quark is the same type of string vibrating in a different mode. A photon, the particle of light, is yet another vibration. This single idea has the potential to unify all of particle physics under one elegant framework, replacing the somewhat arbitrary collection of fundamental particles in the standard model with a single type of object whose richness comes entirely from the way it moves. The shift from points to strings may sound modest, but its consequences ripple through every corner of theoretical physics, reshaping our understanding of gravity, quantum mechanics, and the very fabric of space and time. A single string may be so small that if an atom were the size of Earth, the string would still be invisible. The strings proposed by string theory exist at an almost inconceivably tiny scale. They are thought to have a length of roughly the Planck length, approximately 10 to the power of minus 35 meters. To put that in perspective, an atom is already far too small to see with the naked eye, yet a string is to an atom what an atom is to a star. If you could magnify an atom to the size of the entire planet Earth, a single string would still be too small to see, hidden far below the limit of any conceivable microscope. This extraordinary smallness is both the theory's greatest challenge and one of its most elegant features. Because strings operate at such a tiny scale, they naturally incorporate the effects of quantum gravity, which only become important at distances near the Planck length. No experiment we have built or are likely to build in the near future can probe these scales directly. The strings, if they exist, hum in a realm of reality far beneath anything our instruments can reach, a hidden world of vibration at the very bottom of existence. Each possible vibration of a string maps to a different particle, from electrons to photons. One of the most captivating aspects of string theory is the way it explains the diversity of particles in the universe. In the standard model of particle physics, each type of particle, electrons, quarks, neutrinos, photons, gluons, and so on, is treated as a separate fundamental entity with its own set of properties. String theory replaces this catalog with a single underlying object, the string, and derives all of these particles from its different modes of vibration. A string vibrating in one pattern carries the mass and charge of an electron. The same string vibrating in a different pattern becomes a quark. Yet another vibration gives rise to a photon. The analogy with musical instruments is irresistible. A single violin string can produce an enormous range of notes, and in a similar way, a single fundamental string can produce the entire spectrum of particles we observe in nature. This unification is deeply satisfying because it suggests that the apparent complexity of the particle zoo is not fundamental but emergent, arising from the simple physics of a vibrating filament. One special vibration corresponds to the graviton, the hypothetical particle of gravity. Among all the vibrations a string can perform, one stands out as particularly significant. It is the vibration that produces a massless particle with a spin of 2, and this is precisely the set of properties that the graviton, the hypothetical carrier of the gravitational force, is predicted to have. The graviton has never been detected directly because gravity is extraordinarily weak at the quantum level, but its existence is implied by any quantum theory of gravity. What makes string theory remarkable is that the graviton is not added to the theory by hand. It appears automatically as a natural consequence of the mathematics of vibrating strings. This was one of the earliest and most exciting discoveries in string theory, and it transformed the field from a failed model of nuclear physics into a potential theory of quantum gravity. No other framework produces the graviton so naturally. In a sense, string theory was born with gravity already built in, a feature that has kept physicists fascinated for decades. Some strings form endless closed loops, while others dangle open with free ends. Strings in string theory come in two basic topological varieties. Closed strings form continuous loops with no endpoints, like tiny rubber bands vibrating in higher dimensional space. Open strings, by contrast, have two distinct endpoints that are free to move or may be anchored to larger objects called branes. The distinction between open and closed strings has profound physical consequences. Closed strings naturally give rise to gravity because the graviton emerges from their vibrational spectrum. Open strings, on the other hand, tend to produce the particles associated with the other forces of nature, such as photons and gluons. This elegant division means that the two great categories of physics, gravity and the gauge forces, arise from the two simplest topological configurations a string can take. Open and closed strings can also interact with each other. An open string can join its endpoints to become a closed string, and a closed string can split open. These interactions are governed by smooth, well-defined mathematics, free of the troublesome infinities that plague point-particle theories. Gravity emerges naturally from closed strings, making string theory unique among quantum models. In most approaches to quantum mechanics, gravity is an outsider. The standard model of particle physics describes the electromagnetic, strong nuclear, and weak nuclear forces with extraordinary precision, but it has no place for gravity. Attempts to force gravity into the quantum framework using the same techniques that work for the other forces lead to mathematical disasters, producing infinite answers that cannot be tamed. String theory sidesteps this problem entirely. Because the graviton appears naturally in the vibrational spectrum of closed strings, gravity is not an afterthought, but an integral part of the theory from the very beginning. This makes string theory unique among all known approaches to quantum physics. No other framework produces gravity so organically. The smooth, extended nature of the string spreads out the interactions that would cause infinities if gravity were carried by point particles, resulting in calculations that remain finite and well-behaved. This built-in compatibility with gravity is one of the strongest arguments in favor of string theory, and the primary reason it has attracted so much attention as a candidate for a theory of everything. The theory was first discovered by accident while physicists studied nuclear forces in the 1960s. The origins of string theory are wonderfully accidental. In the late 1960s, physicists were struggling to understand the strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei. A young Italian physicist named Gabriele Veneziano noticed that a mathematical formula originally developed by the 18th century mathematician Leonhard Euler seemed to fit certain patterns observed in particle collisions. It was an unexpected and puzzling connection. Shortly afterwards, other physicists realized that Veneziano's formula could be interpreted as describing the behavior of tiny vibrating strings rather than point particles. This was the birth of string theory, though at the time nobody imagined it would grow into a candidate for a unified theory of all fundamental forces. The original string model was eventually abandoned as a description of the strong force, because quantum chromodynamics proved to be a better fit. But the mathematical beauty and internal consistency of the string framework refused to die, and within a few years, physicists began to recognize that it might be pointing towards something far deeper. What began as a failed model of particle physics grew into a candidate for a theory of everything. The journey of string theory from a discarded model of the strong nuclear force to one of the most ambitious frameworks in all of physics is one of the most remarkable stories in modern science. When the original string model failed to compete with quantum chromodynamics as a description of the strong force, it might have been forgotten entirely. But a handful of physicists noticed that the theory contained a massless spin-2 particle in its spectrum, and they recognized this as the graviton. Rather than being a flaw, this was an extraordinary gift. It meant that string theory naturally included gravity, the one force that had resisted all previous attempts at quantization. This discovery transformed the theory's identity. It was no longer a model of nuclear physics. It was a potential theory of everything, a framework capable of unifying all four fundamental forces and all known particles within a single mathematical structure. The ambition of this goal is breathtaking. A theory of everything would explain not just how particles interact, but why the universe has the laws it does. And string theory remains the most developed candidate for achieving that dream. String theory insists that the universe has hidden dimensions beyond the three of space and one of time. One of the most startling predictions of string theory is that the universe contains more dimensions than we can perceive. In our everyday experience, we move through three dimensions of space, left and right, forward and backward, up and down, and we experience one dimension of time. But string theory's equations simply do not work in four-dimensional spacetime. They demand additional dimensions, hidden directions of space that we cannot see or feel. The idea of extra dimensions is not entirely new. It was first proposed in the 1920s by Theodore Kaluza and Oscar Klein, who showed that a fifth dimension could help unify gravity and electromagnetism. String theory takes this idea much further, requiring 6 or 7 extra dimensions depending on the version of the theory. These hidden dimensions are not optional extras or mathematical curiosities. They are essential for the internal consistency of the theory. Without them, the equations produce nonsensical results, including negative probabilities and broken symmetries. The existence of these dimensions remains unproven, but their necessity within the mathematics is absolute. Most versions require a total of 10 dimensions for the equations to make sense. The most widely studied versions of string theory, including Type I, Type IIA, Type IIB, and the two heterotic string theories, all require spacetime to have exactly 10 dimensions for the mathematics to be consistent. This means 9 dimensions of space and 1 of time. The requirement is not arbitrary. It emerges from deep constraints on the quantum behavior of strings, particularly the need to avoid anomalies, which are mathematical inconsistencies that would render the theory meaningless. In 10 dimensions, these anomalies cancel precisely, and the theory becomes self-consistent. In any other number of dimensions, the cancellations fail. The 6 extra spatial dimensions beyond the 3 we observe are assumed to be compactified, meaning they are curled up into shapes so small that they escape detection by any current experiment. The precise geometry of these compactified dimensions has enormous consequences, potentially determining the masses of particles, the strengths of forces, and the overall structure of the laws of physics we observe. 10 dimensions may seem extravagant, but within the logic of string theory, they are not a luxury. They are a necessity. In a deeper extension known as M-theory, the universe may have 11 dimensions. In the mid-1990s, the physicist Edward Witten proposed that the 5 known versions of string theory were not separate theories at all, but different perspectives on a single, deeper framework that he called M-theory. This underlying theory lives in 11 dimensions, 10 of space and 1 of time, adding 1 more spatial dimension to the 10 required by the original string theories. The 11th dimension changes the character of the theory in profound ways. In M-theory, the fundamental objects are not just strings, but also higher dimensional membranes, including 2-dimensional sheets and higher dimensional volumes. The extra dimension provides the room needed for these extended objects to exist and interact. Witten's proposal was revolutionary because it unified what had seemed like 5 competing theories into a single coherent picture. The various string theories turned out to be different limiting cases of M-theory, each valid in a particular regime of the theory's parameters. The full structure of M-theory remains only partially understood, and its complete formulation is one of the greatest unsolved problems in theoretical physics. But even in its incomplete form, it has reshaped the landscape of fundamental physics. These hidden dimensions are thought to be curled up so tightly that no experiment has yet seen them. If the universe truly has extra dimensions, the obvious question is why we cannot see them. The answer proposed by string theory is that these additional dimensions are compactified, meaning they are curled up into shapes so incredibly small that they are far below the resolution of any instrument we possess. Imagine a garden hose viewed from a great distance. It appears to be a one-dimensional line, but if you could look closely, you would see that it has a second dimension, a tiny circle wrapping around its circumference. In the same way, at every point in our familiar three-dimensional space, there may be 6 or 7 additional directions curled up into a minuscule geometric shape. These shapes are thought to have a diameter near the Planck length, roughly 10 to the power of minus 35 meters, making them utterly invisible to current experiments. The Large Hadron Collider can probe distances down to about 10 to the power of minus 19 meters, which is still 16 orders of magnitude too large to see the extra dimensions. Until technology advances by an almost unimaginable degree, the hidden dimensions of string theory will remain precisely that, hidden. The shapes of these curled-up dimensions could decide the laws of physics we observe. One of the most profound implications of string theory is that the geometry of the hidden dimensions is not merely a mathematical detail, but may actually determine the laws of physics in our observable universe. The masses of particles, the strengths of the fundamental forces, the number of generations of matter, and even whether the universe contains dark energy could all be consequences of the precise shape into which the extra dimensions are folded. Different shapes would produce different physical constants and different sets of particles, meaning that the laws of physics are not truly fundamental, but are instead determined by the geometry of an unseen internal space. This idea represents a dramatic shift in how we think about the laws of nature. Rather than being written into the fabric of reality from the beginning, they may be emergent properties of a deeper geometric structure. The challenge, of course, is that we do not yet know which shape the extra dimensions take, and the number of possible shapes is astronomically large. Finding the right one, if it exists, remains one of the great quests of modern theoretical physics. One possible shape, a Calabi-Yau manifold, twists space into intricate folds beyond imagination. Among the many possible shapes that the extra dimensions could take, one class of geometric objects has received the most attention. These are called Calabi-Yau manifolds, named after the mathematicians Eugenio Calabi and Xingtung Yau. A Calabi-Yau manifold is a 6-dimensional space with very specific geometric properties, including a special kind of curvature that allows supersymmetry to be preserved in the 4-dimensional world we observe. These shapes are extraordinarily complex, with intricate folds, holes, and twists that defy ordinary visualization. Even the simplest Calabi-Yau manifolds have hundreds of parameters describing their geometry, and each different configuration would produce a different set of physical laws. Computer-generated images of these manifolds reveal stunningly beautiful objects, with smooth surfaces curving through 6 dimensions in ways that resemble organic forms or abstract sculptures. The topology of a Calabi-Yau manifold, including the number and type of its holes, determines things like the number of particle families and the pattern of symmetries we observe. These hidden shapes, curled up at every point in the universe, may be the secret architects of everything we see. Strings can stretch, twist, and vibrate in countless ways, each way revealing a new type of matter or force. The richness of string theory arises from the extraordinary versatility of its fundamental objects. A string is not rigid or fixed. It can stretch, contract, twist, fold, and oscillate in a vast number of different patterns. Each distinct pattern of vibration corresponds to a different physical entity, a different particle with its own unique mass, charge, spin, and other quantum properties. The number of possible vibrational modes is essentially infinite, though most of them correspond to particles with masses so enormous that they would only have existed in the extreme conditions of the very early universe. The particles we observe today, the lightweight electrons, quarks, and photons, correspond to the lowest energy vibrations of the string. Higher energy modes produce progressively heavier particles that lie far beyond the reach of current accelerators. This tower of increasingly massive states is one of string theory's distinctive predictions. The idea that all of nature's diversity can be traced back to the different ways a single type of object can vibrate is both simple and profound, a reminder that complexity can emerge from the simplest of foundations. The vibrational patterns of strings could explain why electrons, quarks, and photons are all so different. In the standard model of particle physics, electrons, quarks, and photons are treated as entirely different types of fundamental particles, each with its own set of properties and governed by its own set of rules. There is no deeper explanation for why these particles have the masses, charges, and spins they do. The values are simply measured and plugged into the equations. String theory offers a potential explanation. If all particles are different vibrations of the same fundamental string, then the differences between them are not arbitrary, but are determined by the geometry and dynamics of the vibrating string. The mass of a particle depends on how energetically the string vibrates. Its charge depends on the pattern of the vibration. Its spin depends on the rotational mode. This means that the properties we observe are not free parameters, but are in principle calculable from the underlying theory. The dream of string theory is to derive the entire particle spectrum, including the masses and coupling constants, from first principles. While this goal has not yet been achieved, the theoretical framework for doing so is in place, and the vision remains one of the most compelling in all of physics. Strings are measured at the Planck length, a scale far smaller than anything we can probe. The Planck length is a natural unit of distance derived from three fundamental constants of nature: the speed of light, the gravitational constant, and Planck's constant. It works out to approximately 10 to the power of minus 35 meters, a distance so unimaginably small that it makes even subatomic particles seem enormous by comparison. This is the scale at which quantum effects are expected to dominate the behavior of gravity, and it is the scale at which strings in string theory are thought to exist. To appreciate just how small this is, consider that a proton, one of the building blocks of atomic nuclei, is about 10 to the power of minus 15 meters across. The Planck length is 20 orders of magnitude smaller than that. If you could line up Planck length strings side by side, you would need more of them to span a single proton than you would need protons to span the observable universe. This vast gulf between the Planck scale and the scales accessible to experiment is one of the central challenges facing string theory. The strings may be real, but they vibrate at a depth of reality that seems forever beyond our direct reach. At this scale, space-time itself may dissolve into quantum foam, softened by the smoothness of strings. At distances near the Planck length, the familiar smooth fabric of space-time is expected to break down. According to quantum mechanics, the vacuum of space is not truly empty, but seethes with virtual particles and energy fluctuations. At the Planck scale, these fluctuations become so violent that space-time itself is thought to dissolve into a churning, turbulent state, often called quantum foam. In theories based on point particles, this foam creates insurmountable mathematical problems, producing infinite answers and rendering calculations meaningless. String theory offers a natural solution. Because strings have a finite length, they smooth out the most violent fluctuations, preventing the equations from encountering the infinities that plague point-particle approaches. The extended nature of the string acts as a built-in regulator, softening the geometry of spacetime at the smallest scales and replacing the jagged, foamy landscape with something more gentle and mathematically tractable. This smoothing effect is not imposed from outside, but emerges naturally from the physics of the string itself. It is one of the most elegant features of the theory and a key reason why string theory succeeds where other approaches to quantum gravity have failed. By replacing points with loops, string theory avoids the catastrophic infinities that plague other quantum theories of gravity. One of the deepest problems in 20th century physics was the incompatibility between general relativity and quantum mechanics. When physicists tried to combine them by treating gravity as a quantum force carried by point-like particles called gravitons, the resulting calculations produced infinite answers at every turn. The infinities arose because point particles can collide at a single point in space, creating interactions of infinite density and energy. String theory resolves this problem by replacing point particles with tiny loops and filaments of finite extent. When two strings interact, they do not collide at a single point. Instead, they merge and split smoothly, like two soap bubbles joining and separating. This smooth interaction spreads the energy of the encounter over a finite area, preventing the dangerous concentration of energy at a point. The result is a theory of quantum gravity in which calculations remain finite and well-defined. This taming of the infinities is one of string theory's most celebrated achievements, and the feature that first convinced many physicists that the theory was worth pursuing seriously. The theory also predicts extended objects called branes, which can stretch across higher dimensions. Strings are not the only objects in string theory. As the theory developed, physicists discovered that it also predicts higher dimensional objects called branes, short for membranes. A brane can have any number of spatial dimensions. A zero brane is a point, a one brane is a string, a two brane is a sheet or membrane, and so on, up to the full number of spatial dimensions in the theory. These objects are not incidental curiosities. They play essential roles in the dynamics of string theory, serving as surfaces on which open strings can end, as sources of gravitational and other fields, and as building blocks for constructing realistic models of the universe. The discovery of branes was one of the key developments of the 1990s and played a central role in the unification of the 5 string theories into M theory. Branes can move, vibrate, and interact with each other in the higher dimensional space, and their behavior can give rise to rich and complex physics. In some models, our entire observable universe is itself a 3-dimensional brane floating in a higher dimensional space. Branes can come in many forms, from 2-dimensional sheets to volumes that fill entire universes. The variety of branes predicted by string theory is remarkable. A 2-brane or membrane is a 2-dimensional surface that can extend across the higher dimensional space like a vast, rippling sheet. A 3-brane has 3 spatial dimensions, the same number as the space we inhabit, which immediately suggests a tantalizing possibility. Our entire universe might be a 3-brane. Higher dimensional branes can fill even larger volumes of the ambient space. The properties of each type of brane are determined by its dimensionality, its tension, and the types of fields that live on its surface. Some branes are stable and can exist indefinitely, while others are unstable and decay into lower dimensional objects. The interactions between branes of different dimensionalities give rise to a rich tapestry of physical phenomena, including the appearance and disappearance of particles, the generation of forces, and the formation of complex geometric structures. The study of brains has become one of the most active areas of research in string theory, revealing connections between gravity, gauge theories, and even condensed matter physics that would never have been anticipated without the brain framework. Our entire cosmos may be a three-dimensional brain floating in a higher dimensional space. One of the most dramatic ideas to emerge from string theory is the brain world scenario, the proposal that our entire observable universe is a three-dimensional brain embedded in a larger, higher dimensional space called the bulk. In this picture, the particles of the standard model, including electrons, quarks, and photons, are open strings whose endpoints are confined to our brain, which is why we cannot escape into the extra dimensions. Gravity, however, is carried by closed strings, which have no endpoints and are therefore free to propagate into the bulk. This provides a natural explanation for one of the oldest puzzles in physics: why gravity is so much weaker than the other forces. If gravity leaks into the extra dimensions while the other forces remain confined to our brain, its apparent strength in our three-dimensional world would be diluted. The brainworld idea also opens the door to exotic possibilities, including the existence of other brains, parallel to ours, floating in the same bulk, each potentially hosting its own universe with its own laws of physics. It is a vision of reality that is both humbling and exhilarating. Gravity might leak off our brain into extra dimensions, explaining why it feels so weak compared to other forces. Gravity is by far the weakest of the four fundamental forces. A tiny refrigerator magnet can overcome the gravitational pull of the entire planet Earth, which gives some sense of the enormous disparity between gravity and the electromagnetic force. This weakness has long puzzled physicists, and string theory offers an elegant potential explanation through the brainworld scenario. If our universe is a three-dimensional brain in a higher dimensional bulk, and if gravity, carried by closed strings, can propagate into the extra dimensions while the other forces are confined to our brain, then gravity's apparent weakness could be a geometric illusion. The gravitational force would spread out into additional dimensions, diluting its strength from our perspective, while the other forces, trapped on the brain, would retain their full intensity. Models based on this idea have been explored by physicists including Lisa Randall and Raman Sundaram, who showed that a warped extra dimension could explain the hierarchy between gravity and the other forces without requiring fantastically large extra dimensions. The idea remains speculative, but it is one of the most creative applications of extra-dimensional physics. Strings with open ends can be tethered to brains, shaping how matter behaves. Open strings in string theory have two endpoints, and these endpoints are not free to float wherever they please. They must be attached to brains, the higher dimensional objects that populate the theory. This constraint has profound consequences for the physics that emerges. The type of brain to which an open string is attached determines the forces and particles that string can produce. If both endpoints of a string are attached to the same brain, the string's vibrations give rise to particles that live on that brain. If the two endpoints are attached to different brains, the string stretches between them, and its vibrations produce particles whose mass depends on the distance between the brains. This mechanism provides a natural way to generate the mass spectrum of particles, connecting the geometry of the extra dimensions to the observed masses of quarks, leptons, and force carriers. The interplay between open strings and brains is one of the most powerful features of string theory, allowing the construction of models that resemble the standard model of particle physics. Brains are not passive backgrounds. They are active participants in the physics, shaping the behavior of matter in fundamental ways. When brains collide, they may release bursts of energy on a cosmic scale. In the higher dimensional bulk of string theory, brains are dynamical objects that can move, oscillate, and collide with each other. When two brains come into contact, the collision can release an enormous amount of energy, potentially on a scale comparable to the most energetic events in the history of the universe. This idea has been explored in cosmological models as a possible mechanism for generating the energy of the Big Bang itself. In such scenarios, the hot, dense state from which our universe expanded was not the beginning of everything, but the result of a collision between two brains in the higher dimensional bulk. The energy liberated by the impact would have heated the brain universe to extreme temperatures, setting in motion the familiar processes of cosmic expansion, nucleosynthesis, and structure formation. Brain collisions could also produce gravitational waves, cosmic strings, and other relics that might, in principle, be observable. While these models are highly speculative, they illustrate the remarkable fertility of the brain concept and its ability to connect the microscopic physics of strings to the largest structures in the cosmos. Some cosmologists believe the Big Bang itself could have been caused by two brains colliding. The ekpyrotic scenario is one of the most adventurous cosmological models inspired by string theory. It proposes that the Big Bang was not the spontaneous creation of the universe from nothing, but the result of a violent collision between two three-dimensional brains moving toward each other through the higher dimensional bulk. The name comes from the ancient Greek word ekpyrosis, meaning conflagration or cosmic fire. In this model, the energy of the collision is converted into the matter and radiation that fill our universe, and the resulting expansion produces a cosmos that closely resembles the one we observe. The ekpyrotic scenario offers an alternative to cosmic inflation, the more widely accepted theory of the very early universe, and it makes subtly different predictions about the patterns of primordial fluctuations in the cosmic microwave background. These differences are small but potentially measurable, meaning that future observations could, in principle, distinguish between the two scenarios. Whether or not the ekpyrotic model proves correct, it demonstrates the power of string theory to generate new ideas about the origin and evolution of the universe. String theory offers the first serious framework that unifies all four fundamental forces of nature. The four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, govern everything that happens in the universe. For most of the 20th century, physicists worked to understand each force individually and then to find connections between them. The electromagnetic and weak forces were successfully unified in the 1960s and 70s, and there are strong theoretical reasons to believe that the strong force joins them at very high energies. But gravity has always stood apart, resisting unification with the other three. String theory is the first framework that brings all four forces together within a single mathematical structure. Gravity emerges from closed strings, while the gauge forces emerge from open strings attached to brains. The coupling constants of each force are determined by the geometry of the extra dimensions. In principle, a complete understanding of the compactified dimensions would allow us to derive the strengths of all four forces from a single underlying theory. This is the dream of unification that has guided physics since Einstein, and string theory remains the most promising vehicle for realizing it. It weaves together electromagnetism, the strong and weak nuclear forces, and gravity itself. The unification of forces in string theory is not merely an assertion, but a consequence of the theory's mathematical structure. Electromagnetism, the force responsible for light, electricity, and magnetism, is carried by the photon. The strong nuclear force, which binds quarks together inside protons and neutrons, is carried by gluons. The weak nuclear force, responsible for certain types of radioactive decay, is carried by the W and Z bosons. And gravity, in the string picture, is carried by the graviton. All of these force-carrying particles emerge as different vibrational modes of strings. In the standard model, each force has its own separate mathematical description, and gravity is not included at all. String theory replaces this patchwork with a single unified framework in which every force arises from the same underlying physics. The key is that the different forces correspond to strings living in different sectors of the theory: open strings on branes for the gauge forces and closed strings propagating freely for gravity. The elegance of this picture is hard to overstate. A single type of object, vibrating in different ways, gives rise to everything from light to gravity. The unification dream was pursued by Einstein for decades, and string theory may finally achieve it. Albert Einstein spent the last 3 decades of his life searching for a unified field theory, a single mathematical framework that would combine gravity and electromagnetism into one coherent picture. He worked on this problem tirelessly from the mid-1920s until his death in 1955, but he never succeeded. At the time, the strong and weak nuclear forces had not yet been fully understood, so the scope of the unification problem was even larger than Einstein realized. In the decades since, the electroweak theory successfully unified electromagnetism with the weak force, and grand unified theories have been proposed to include the strong force. But true unification, the inclusion of gravity alongside the other 3 forces, remained elusive until the development of string theory. By incorporating the graviton as a natural vibration of the string, and by deriving all other forces from the same underlying framework, string theory comes closer to Einstein's dream than any other approach in the history of physics. Whether it ultimately succeeds remains to be seen, but the ambition is worthy of the tradition that Einstein began. Supersymmetry is essential to string theory, pairing every particle with a heavier, unseen partner. Supersymmetry is a mathematical symmetry that relates 2 fundamentally different categories of particles: bosons, which carry forces, and fermions, which make up matter. In a supersymmetric theory, every boson has a corresponding fermionic partner, and every fermion has a corresponding bosonic partner. The electron would be paired with a bosonic particle called the selectron. The photon would be paired with a fermion called the photino. Quarks would be paired with squarks. None of these supersymmetric partners have been observed in experiments, which means that if supersymmetry exists, it must be broken at the energies we can currently probe, making the partners much heavier than their familiar counterparts. Supersymmetry is not an optional feature of string theory. It is built into the very fabric of the theory and is essential for its mathematical consistency. Without supersymmetry, the equations of string theory develop fatal inconsistencies, including the appearance of tachyons, particles that travel faster than light, and signal an instability in the theory. The search for supersymmetric particles at the Large Hadron Collider is one of the most important ongoing tests of ideas related to string theory. These partners, such as the selectron or squark, have not yet been detected in experiments. If supersymmetry is a true symmetry of nature, then every known particle should have a heavier supersymmetric partner waiting to be discovered. The electron's partner, the selectron, the quark's partner, the squark, and the photon's partner, the photino, are just a few examples from a complete mirror family of particles predicted by the theory. Despite decades of searching, none of these particles have been detected. The most powerful particle accelerator in the world, the Large Hadron Collider at CERN, has conducted extensive searches for supersymmetric particles and has so far come up empty. This non-detection does not definitively rule out supersymmetry, because the partners could be heavier than the energies currently accessible, but it does push the theory into an increasingly constrained corner. Each new energy threshold that is crossed without a discovery raises the question of how heavy the supersymmetric partners would need to be, and whether a more natural version of the theory can survive. The absence of evidence is not evidence of absence, as physicists are fond of saying, but the silence from the detectors is becoming harder to ignore. Discovering supersymmetric particles would be one of the strongest confirmations of string theory. While the detection of supersymmetric particles would not prove string theory outright, it would provide a powerful piece of circumstantial evidence in its favor. Supersymmetry is a necessary ingredient of string theory, so finding that nature respects this symmetry would remove one of the major uncertainties hanging over the framework. It would tell us that the type of mathematical structure string theory relies upon is actually realized in the physical world, a finding that would energize the entire field and open new avenues of research. The discovery could also help determine which version of string theory best describes our universe, because different compactification schemes predict different spectra of supersymmetric particles. The masses, spins, and decay patterns of the discovered particles would provide clues about the geometry of the hidden dimensions. Conversely, the continued absence of supersymmetric particles at higher and higher energies would increasingly challenge the most natural versions of string theory, though it would not rule out the theory entirely, since supersymmetry could be broken at scales beyond our current reach. The stakes of these experimental searches, therefore, extend far beyond the particles themselves. Supersymmetry also cancels dangerous quantum instabilities that would otherwise wreck the theory. Without supersymmetry, string theory suffers from a number of severe mathematical problems. One of the most serious is the appearance of tachyons in the spectrum, hypothetical particles that would travel faster than light and whose presence signals a fundamental instability in the vacuum of the theory. A vacuum containing tachyons is like a ball balanced on the peak of a hill. Any tiny disturbance would send it rolling downward into an unknown and potentially catastrophic state. Supersymmetry eliminates the tachyons by ensuring that the dangerous contributions from bosons and fermions cancel each other precisely, stabilizing the vacuum and making the theory mathematically consistent. This cancellation is not approximate or fine-tuned. It is exact, a consequence of the deep symmetry between the bosonic and fermionic sectors of the theory. Supersymmetry also tames other quantum instabilities, including divergences in loop diagrams that would otherwise produce infinite corrections to physical quantities. The role of supersymmetry in maintaining the health of the theory is so fundamental that it is difficult to imagine string theory surviving without it. In this sense, supersymmetry is not merely a desirable feature. It is the backbone of the entire framework. Without supersymmetry, string theory's equations simply cannot remain consistent. The mathematical consistency of string theory depends critically on the presence of supersymmetry. Without it, the theory develops anomalies, which are breakdowns in the symmetries that the theory needs to function. These anomalies lead to violations of conservation laws, negative probabilities, and other pathological features that make the theory physically meaningless. The requirement for supersymmetry is not an aesthetic preference or a convenient simplification. It is a non-negotiable structural demand of the mathematics. When physicists tried to construct versions of string theory without supersymmetry in the early days of the field, they quickly encountered insurmountable problems. The bosonic string theory, which has no supersymmetry, lives in 26 dimensions, contains tachyons, and does not include fermions, the particles that make up matter. It is mathematically interesting, but physically unrealistic. Only by introducing supersymmetry could the theory be brought into a form that includes both bosons and fermions, lives in a more reasonable number of dimensions, and avoids tachyonic instabilities? This intimate dependence on supersymmetry is both a strength and a vulnerability, because it ties the fate of the theory to a symmetry that has not yet been confirmed by experiment. Over time, physicists discovered that there are several kinds of string theory. As string theory developed through the 1970s and 80s, it became clear that the framework was not a single theory, but a family of related theories, each with its own distinctive features. Physicists eventually identified 5 consistent versions of superstring theory, each living in 10 spacetime dimensions and each incorporating supersymmetry, but differing in the types of strings they contain and the symmetries they obey. This multiplicity was initially seen as a problem. If string theory was supposed to be the unique theory of everything, why were there 5 versions of it? The situation was compared to arriving at the summit of a mountain only to find 5 separate peaks, each claiming to be the true top. The resolution of this puzzle would come later, with the discovery of dualities and the proposal of M-theory. But for a time, the existence of multiple string theories cast doubt on the uniqueness of the framework and led to vigorous debates about which version, if any, described the real world. In retrospect, the multiplicity turned out to be a feature rather than a flaw, revealing a deeper structure that unified them all. These include type I, type IIA, type IIB, and 2 heterotic versions. The 5 consistent superstring theories are known as type I, type IIA, type IIB, heterotic SO32, and heterotic E8 times E8. Each has its own character. Type I contains both open and closed strings and has a specific gauge symmetry group. Type IIA and type IIB contain only closed strings and differ in the way their left-moving and right-moving vibrations are related by supersymmetry. The 2 heterotic theories are perhaps the most unusual, combining a supersymmetric right-moving sector with a bosonic left-moving sector. This asymmetric construction gives the heterotic strings their distinctive gauge symmetry groups, which happen to be large enough to contain the symmetries of the standard model. In the 1980s, the heterotic E8 times E8 theory was considered the most promising candidate for describing the real world, because its gauge group naturally accommodated grand unified theories. As the field evolved, attention shifted between the different versions, and the eventual discovery that all 5 are connected by dualities transformed the landscape of the subject. Each of the 5 theories turned out to be a different window onto the same underlying structure. At first, they seemed like competing and contradictory possibilities. When the 5 superstring theories were first identified, the situation seemed deeply unsatisfying. A theory that aspired to be the unique description of all physical reality existed in 5 apparently distinct versions, each with its own set of rules and its own predictions. Physicists debated which version was correct, and some worried that the multiplicity undermined the entire program. If any of the 5 could describe a consistent universe, how could string theory claim to be uniquely predictive? The theories shared many features, including the requirement for 10 dimensions and the inclusion of supersymmetry, but they differed in important details, such as the types of strings they contained and the gauge symmetries they predicted. For a time, it seemed as though the dream of a unique theory of everything might be an illusion, replaced by a menu of options with no clear way to choose among them. This period of uncertainty was intellectually uncomfortable, but ultimately productive. It set the stage for one of the most dramatic developments in the history of theoretical physics, the discovery that these 5 theories were not separate at all, but different faces of a single deeper framework. Then came the realization that they were secretly linked by hidden dualities. The breakthrough that transformed string theory came in the mid-1990s, when physicists began to discover a web of mathematical relationships called dualities that connected the 5 superstring theories to each other. A duality is a precise mathematical equivalence between 2 theories that appear different on the surface, but describe exactly the same physics. The first and most famous of these was T-duality, which showed that a theory compactified on a large circle is equivalent to a different theory compactified on a small circle. Then came S-duality, which related the strong coupling regime of one theory to the weak coupling regime of another. These dualities meant that the 5 theories were not competing alternatives, but different descriptions of the same underlying reality, each valid in a different regime of the theory's parameter space. The discovery of these hidden connections was electrifying, transforming the fragmented landscape of string theory into a unified web. It showed that what had seemed like a weakness, the existence of multiple versions, was actually a strength, revealing the extraordinary depth and interconnectedness of the framework. These dualities showed that what looks like one theory in one regime is another theory in disguise. The concept of duality in string theory is both simple and profound. It tells us that 2 descriptions that look completely different, involving different numbers of dimensions, different types of strings, or different strengths of interaction, can be mathematically equivalent, meaning they make identical predictions for every observable quantity. T-duality, for example, shows that a theory with a tiny compactified dimension is physically indistinguishable from a theory with a very large compactified dimension. S-duality shows that a theory where strings interact very strongly is equivalent to a different theory where strings interact very weakly. These equivalences are not approximate. They are exact, holding at every level of precision. The implication is startling. What appears to be a fundamental feature of one theory, such as the size of a dimension or the strength of a coupling, may be an emergent feature from the perspective of a dual theory. This suggests that many of the quantities we consider fundamental may be artifacts of our particular description rather than intrinsic properties of reality. Duality teaches us that the universe may be far more symmetric and interconnected than any single description can reveal. This surprising web of connections led to the birth of M-theory. The discovery that the 5 superstring theories were connected by dualities raised an obvious question. If they are all different aspects of a single underlying theory, what is that theory? In 1995, at a conference at the University of Southern California, Edward Witten proposed that all 5 string theories and 11-dimensional supergravity are limiting cases of a single, deeper framework that he tentatively called M-theory. The proposal was bold because M-theory itself was not yet fully defined. Witten and others could describe its properties in various limiting regimes, but the complete, non-perturbative formulation remained, and still remains, elusive. What was clear was that M-theory lives in 11 dimensions, includes both strings and higher-dimensional branes as fundamental objects, and reduces to each of the 5 string theories when certain parameters are taken to particular values. The announcement electrified the physics community and launched what became known as the second superstring revolution. M-theory remains the most ambitious theoretical construct in the history of physics, a framework that aspires to encompass all of reality within a single mathematical structure. M-theory suggests that all string theories are just different limits of one deeper framework. The central claim of M-theory is extraordinarily elegant. The 5 apparently distinct superstring theories are not 5 competing candidates for the theory of everything, but rather 5 different windows onto a single underlying structure. Each string theory emerges when certain parameters of M-theory are taken to particular limiting values, much as ice, liquid water, and steam are different phases of the same substance. In one limit, M-theory looks like type IIA string theory. In another, it looks like the heterotic E8 times E8 theory. In yet another, it reduces to 11-dimensional supergravity. The complete M theory, valid at all parameter values simultaneously, has never been fully formulated, and writing down its fundamental equations remains one of the greatest open problems in theoretical physics. What physicists do know is that M theory lives in 11 spacetime dimensions, contains both strings and higher dimensional objects called branes, and possesses a rich web of symmetries that constrain its behavior. The vision that all of fundamental physics could emerge from the limits of a single master theory is breathtaking, and it continues to guide research decades after its proposal. In M theory, strings themselves may be slices of larger objects called membranes. One of the most striking features of M theory is that the fundamental one-dimensional strings of string theory are not truly fundamental at all. In 11 dimensions, the basic objects include two-dimensional membranes, often called M2 branes, and five-dimensional objects called M5 branes. When one of the 11 dimensions is compactified into a tiny circle, an M2 brane wrapped around that circle appears, from the 10-dimensional perspective, as a one-dimensional string. In this way, the strings that give string theory its name are revealed to be cross-sections of a higher dimensional membrane, much as a circle is a cross-section of a cylinder. This insight fundamentally changed the way physicists think about the basic building blocks of the theory. Strings are no longer the most primitive objects. They are emergent, arising from the geometry of the extra dimensions and the wrapping of branes. The discovery that strings are slices of membranes was one of the key insights that motivated the proposal of M theory in the first place, and it illustrates how higher dimensional thinking can reveal hidden structures that are invisible from a lower dimensional vantage point. The M in M theory has been said to stand for magic, mystery, or mother. When Edward Witten introduced M theory, he was deliberately vague about what the letter M stood for. Over the years, physicists have suggested many possibilities, including membrane, master, matrix, mother, magic, and mystery. Witten himself has said that the meaning of the M is for each person to decide, and that it might depend on what M theory ultimately turns out to be. If it is defined by membranes, the M stands for membrane. If it turns out to be the master theory that unifies all of physics, the M stands for master. The playful ambiguity reflects the fact that M theory is not yet fully understood, and its final formulation may reveal a meaning that nobody has yet imagined. This deliberate vagueness has become part of the culture and folklore of the subject, a reminder that the deepest theory in physics remains tantalizingly incomplete. The letter M has become a symbol of both aspiration and humility, representing the grandest ambition in theoretical physics and the honest acknowledgement that we have not yet achieved it. Whatever the M eventually stands for, the theory it names has permanently changed the landscape of fundamental physics. M theory expanded the possible dimensions from 10 to 11. All 5 superstring theories require exactly 10 spacetime dimensions for mathematical consistency, 9 of space and 1 of time. M theory raised this number to 11, adding 1 more spatial dimension to the picture. The 11th dimension was not an arbitrary addition, but a necessary consequence of the dualities connecting the different string theories. When the coupling strength of type IIA string theory is increased, a new spatial dimension opens up, inflating from 0 size to a macroscopic extent, and the 10-dimensional theory becomes 11-dimensional supergravity. The existence of this 11th dimension had been suspected since the early 1980s, when supergravity in 11 dimensions was shown to be a uniquely elegant theory, but it had fallen out of favor when it was realized that supergravity alone could not serve as a complete quantum theory of gravity. M-theory rehabilitated 11 dimensions by embedding supergravity within a larger quantum framework. The 11th dimension also provides the space in which higher dimensional brains live and interact, giving M-theory its rich and complex structure. The expansion from 10 to 11 dimensions was a conceptual leap that unified the 5 string theories and opened an entirely new chapter in the quest for the fundamental laws of nature. The discovery of dualities was so revolutionary it became known as the second superstring revolution. The first superstring revolution, in 1984, established string theory as a serious candidate for a unified theory of physics and attracted a generation of brilliant minds to the field. The second superstring revolution, beginning in 1995, was triggered by the discovery of dualities and the proposal of M-theory. It transformed the subject even more profoundly than the first. The second revolution revealed that the 5 string theories were different aspects of a single framework, introduced brains as fundamental objects alongside strings, gave birth to the holographic principle, and inspired the celebrated AD-SCFT correspondence. The pace of discovery during this period was extraordinary, with major papers appearing almost weekly and entire subfields springing into existence overnight. The tools developed during the second revolution extended far beyond string theory, influencing pure mathematics, condensed matter physics, and quantum information science. This period demonstrated that string theory was not a static or stagnant enterprise, but a vibrant and evolving program capable of producing deep surprises. The second superstring revolution remains one of the most productive and intellectually exciting episodes in the history of modern physics. String theory gave birth to the holographic principle, one of the most radical ideas in physics. The holographic principle is the idea that all the information contained within a region of space can be described by a theory that lives on the boundary of that region. In other words, the three-dimensional world we experience may be a kind of projection from a two-dimensional surface, much as a hologram on a flat piece of film can encode a three-dimensional image. This astonishing idea emerged from the study of black holes in string theory. When physicists calculated how much information a black hole can store, they found that it depends not on the volume of the black hole, but on the area of its event horizon. This suggested that the fundamental degrees of freedom of a gravitational system are not distributed throughout its volume, but are encoded on its boundary. The holographic principle, first articulated by Gerard 't Hooft and later refined by Leonard Susskind, challenges our most basic intuitions about space and reality. It implies that the universe may have fewer fundamental dimensions than we perceive, and that what we experience as the depth and richness of three-dimensional space is a kind of elaborate encoding from a lower dimensional surface. The holographic principle suggests that everything in the universe may be encoded on a distant surface. If the holographic principle is correct, then the entire content of a volume of space, every particle, every field, every interaction, can in principle be described by information living on the boundary of that volume. This is a radical departure from the way physics has traditionally been formulated. Normally, we think of physical degrees of freedom as being spread throughout the volume of space, with the number of independent degrees of freedom growing with the volume. The holographic principle says that the true number of degrees of freedom grows only with the area of the boundary, which is a much slower rate. This means that in a deep sense, the interior of a region of space contains less information than you might expect, or equivalently, that the boundary contains far more information than seems possible. The implications extend to cosmology as well. Some physicists have proposed that the visible universe itself may be a holographic projection from its cosmological horizon. While this idea remains speculative, It has inspired a great deal of research and has led to concrete mathematical tools that have been applied to problems in quantum gravity, condensed matter physics, and beyond. This insight first arose from studying black holes in string theory. Black holes have played a central role in the development of string theory, serving as both a testing ground and a source of profound insights. The connection between black holes and the holographic principle began with the work of Jacob Bekenstein and Stephen Hawking in the 1970s. Bekenstein proposed that a black hole has an entropy proportional to the area of its event horizon, and Hawking confirmed this by showing that black holes emit thermal radiation at a specific temperature. These discoveries implied that the information content of a black hole scales with its surface area, not its volume, a deeply puzzling result from the perspective of conventional physics. When string theorists began studying black holes using the tools of their theory, they were able to reproduce Bekenstein and Hawking's results from a microscopic calculation, providing the first concrete evidence that the holographic principle was more than just a conjecture. The study of black holes in string theory also led directly to the AD-SCFT correspondence, one of the most important theoretical developments of the past 3 decades. In this way, black holes have served as a bridge between gravity, quantum mechanics, and the holographic structure of space-time. Black holes seem to destroy information, defying quantum law. One of the deepest puzzles in theoretical physics is the black hole information paradox. When matter falls into a black hole, it appears to be lost forever, trapped behind the event horizon from which nothing can escape. Yet quantum mechanics insists that information can never be truly destroyed. Every process in quantum physics is, in principle, reversible, meaning that the complete information about any initial state can always be recovered from the final state. A black hole that swallows information and then evaporates away through Hawking radiation seems to violate this fundamental principle, because the radiation appears to be perfectly thermal and featureless, carrying none of the detailed information about what fell in. Stephen Hawking originally argued that black holes do destroy information, a conclusion that would require a radical modification of quantum mechanics. Most physicists found this deeply troubling and suspected that the information must be preserved somehow. The resolution of this paradox has been one of the driving forces behind developments in string theory and quantum gravity, pushing theorists to reconsider basic assumptions about the nature of space-time, horizons, and the encoding of information. But string theory showed that information could be preserved on the horizon like a hologram. String theory offered a resolution to the black hole information paradox by showing that the information swallowed by a black hole is not lost, but is encoded on the event horizon in a scrambled and highly non-local form. From the perspective of an outside observer, every bit of information that falls into the black hole is smeared across the surface of the horizon, preserved in a manner analogous to the way a hologram encodes a 3-dimensional image on a 2-dimensional surface. When the black hole eventually evaporates through Hawking radiation, this information is gradually released back into the universe, subtly imprinted in the correlations between the emitted quanta. The process is extraordinarily slow, and the information is scrambled beyond recognition, but in principle, nothing is lost. This picture was supported by calculations in string theory that showed the microscopic states of a black hole are consistent with the preservation of information. Leonard Susskind and Gerard Hooft played key roles in developing this understanding, which became known as black hole complementarity. The resolution demonstrated that string theory could address some of the deepest conceptual puzzles in physics, reinforcing confidence in the framework. This inspired the famous AD-SCFT correspondence, linking gravity to quantum field theory. The AD-SCFT correspondence proposed by Juan Maldacena in 1997, is widely regarded as one of the most important theoretical discoveries in the history of physics. It establishes a precise mathematical equivalence between a gravitational theory in a curved space called anti-de Sitter space and a non-gravitational quantum field theory living on the boundary of that space. In the simplest version, a superstring theory in a five-dimensional anti-de Sitter space times a five-dimensional sphere is exactly equivalent to a supersymmetric gauge theory in four flat dimensions. This duality is remarkable because it connects two seemingly unrelated frameworks, one that includes gravity and one that does not, allowing calculations that are impossible in one framework to be performed in the other. Problems in strongly coupled quantum field theory, which are notoriously difficult, can be translated into tractable problems in classical gravity. Conversely, puzzles in quantum gravity, such as the black hole information paradox, can be reformulated in the language of quantum field theory. The AD-SCFT correspondence has inspired thousands of papers and influenced fields ranging from nuclear physics to condensed matter, making it one of the most versatile tools in modern theoretical physics. AD-SCFT showed that a string theory in a curved space can be exactly equivalent to a field theory on its boundary. The technical content of the AD-SCFT correspondence is both precise and astonishing. It says that every physical observable in a string theory living in the interior of an anti-de Sitter space has a corresponding observable in a conformal field theory living on the boundary of that space, and that the two give identical results. The interior is sometimes called the bulk, and the boundary is a lower dimensional surface that wraps around it. A massive object in the bulk, such as a black hole, corresponds to a particular thermal state in the boundary field theory. A gravitational wave propagating through the bulk corresponds to a disturbance in the boundary theory. The correspondence is holographic in the most literal sense, because all the information about the higher dimensional gravitational interior is completely captured by the lower dimensional non-gravitational boundary. This is not an approximation or a rough analogy. It is an exact mathematical equivalence, confirmed by an enormous body of calculations over more than 2 decades. The AD-SCFT correspondence has given physicists a concrete realization of the holographic principle and has provided the most detailed understanding to date of how gravity can emerge from a non-gravitational quantum system. This duality has been one of the most powerful tools in modern theoretical physics. Since its discovery, the AD-SCFT correspondence has grown far beyond its original setting in string theory to become a universal tool used across many branches of physics. Its power lies in its ability to translate hard problems into easy ones. Strongly coupled quantum systems, which resist all conventional analytical methods, can be mapped into weakly curved gravitational systems where classical calculations apply. This trick has been used to study quark-gluon plasmas, superconductors, quantum phase transitions, and the behavior of strange metals. In each case, the gravitational dual provides insights that would be inaccessible by any other known method. The correspondence has also been applied to questions in quantum information theory, where it has shed light on the nature of entanglement, quantum error correction, and the complexity of quantum states. At the same time, it continues to drive progress in our understanding of quantum gravity, providing a fully consistent quantum mechanical description of certain gravitational systems. No other development in theoretical physics in the past 3 decades has had such a broad and diverse range of applications. It bridges black holes, particle physics, and even condensed matter systems. One of the most remarkable features of the AD-SCFT correspondence is the extraordinary breadth of its applications. In the realm of black holes, it has provided a concrete resolution of the information paradox by showing that the evaporation of a black hole in the bulk corresponds to a perfectly unitary process in the boundary field theory. In particle physics, it has been used to model the strong interactions between quarks and gluons, providing estimates for quantities that cannot be calculated by any other method. In condensed matter physics, it has inspired a new approach to studying strongly correlated electron systems, including high-temperature superconductors and quantum critical phenomena. The tools of holographic duality have even been applied to fluid dynamics, where the equations governing fluids at the boundary can be derived from gravitational equations in the bulk. This cross-pollination between disciplines that were once considered entirely separate is one of the great achievements of modern theoretical physics. The AD-SCFT correspondence has demonstrated that the language of strings and gravity is far more universal than anyone originally imagined, connecting phenomena across vastly different scales and contexts. String theory also explained black hole entropy in precise detail. One of the oldest puzzles in the physics of black holes is the origin of their entropy. In the 1970s, Wittgenstein and Hawking showed that a black hole has an entropy proportional to the area of its event horizon, measured in units of the Planck area. This entropy is enormous, far exceeding the entropy of any ordinary object of the same size. But thermodynamic entropy normally counts the number of microscopic states that a system can occupy, and in the case of a black hole, it was completely unclear what those microscopic states could be. General relativity describes a black hole as a smooth, featureless geometry with no visible internal structure. Where then do the microstates come from? String theory provided the answer. By modeling certain black holes as bound states of strings and branes, Andrew Strominger and Qumran Vafa showed in 1996 that the number of quantum microstates exactly reproduces the Wittgenstein-Hawking entropy formula. This spectacular result was the first microscopic derivation of black hole entropy, and it remains one of the crown jewels of string theory. By counting the microstates of strings and branes, physicists reproduced the exact entropy formula. The Strominger-Vafa calculation was a landmark achievement. They considered a specific type of five-dimensional black hole that could be constructed from a precise combination of d-branes and fundamental strings wrapped around compact dimensions. By counting the number of ways these branes and strings could be arranged while keeping the total mass and charge fixed, they obtained a number that, when taking its logarithm, matched the Wittgenstein-Hawking formula exactly, including the numerical coefficient. This was not an approximate agreement or a rough estimate. It was an exact match, providing overwhelming evidence that string theory correctly captures the microscopic physics of black holes. The calculation was later extended to many other types of black holes, including near-extremal and rotating cases, and in each instance, the agreement held. The success of these calculations demonstrated that string theory could do something no other approach to quantum gravity had achieved, namely to provide a statistical mechanical explanation for the thermodynamic properties of black holes. This accomplishment gave string theorists considerable confidence that they were on the right track, even in the absence of direct experimental confirmation. This was one of the greatest successes of the theory to date. The microscopic derivation of black hole entropy is widely considered to be the single most impressive achievement of string theory. It demonstrated that string theory is not merely a formal mathematical construction, but a physical theory capable of answering deep questions about the nature of gravity and quantum mechanics. Before the Strominger-Vafa calculation, the Bekenstein-Hawking entropy formula was a mysterious thermodynamic result with no known microscopic explanation. After the calculation, it became a precise prediction of string theory, as rigorously derived as the entropy of a gas from statistical mechanics. The result also provided indirect evidence for the existence of D-branes as real physical objects, since the microscopic states that account for the entropy are states of D-branes. Furthermore, the calculation connected concepts from thermodynamics, general relativity, and quantum field theory within a single unified framework, illustrating the extraordinary power of string theory to bridge disparate areas of physics. While critics of string theory sometimes focus on its lack of direct experimental predictions, even the most vocal skeptics generally acknowledge that the black hole entropy calculation is a genuine and significant achievement. It proved that black holes could be understood as collections of strings. The picture that emerged from the microscopic entropy calculations fundamentally changed the way physicists think about black holes. Rather than being featureless, smooth geometries described solely by their mass, charge, and angular momentum, black holes are revealed to be extraordinarily complex quantum objects composed of vast numbers of strings and branes in a tightly bound configuration. The smooth geometry of a black hole is an approximation, an emergent description that arises from averaging over an enormous number of microscopic states. Each distinct configuration of strings and branes represents a different microstate, and the Bekenstein-Hawking entropy counts the logarithm of the total number of such microstates. This perspective has led to the Fuzzball program, an ambitious research effort that aims to construct explicit geometries for individual black hole microstates. In the fuzzball picture, the event horizon is replaced by a quantum structure that differs from microstate to microstate, and there is no interior singularity. While the fuzzball program remains a work in progress, it has demonstrated that string theory has the resources to resolve the internal structure of black holes in unprecedented detail. String theory hints that spacetime itself may not be fundamental. Perhaps the most profound lesson emerging from string theory is that the smooth, continuous spacetime we experience in everyday life may not be a fundamental aspect of reality. Instead, spacetime may be an emergent phenomenon, arising from more primitive quantum mechanical ingredients in much the same way that the temperature of a gas emerges from the collective motion of its molecules. Evidence for this idea comes from several directions within string theory. The AD-SCFT correspondence shows that a gravitational spacetime can be completely reconstructed from a non-gravitational quantum theory that lives on its boundary and makes no reference to spacetime in its fundamental formulation. T-duality shows that the very notion of distance breaks down at the Planck scale, since a tiny dimension and a large dimension can be physically identical. The holographic principle suggests that the three-dimensional space we inhabit may be fully described by information on a two-dimensional surface. Together, these clues paint a picture in which spacetime is not a fixed stage on which physics plays out, but a dynamical, emergent structure that arises from deeper quantum entanglements and correlations. Instead, space and time could emerge from deeper quantum entanglements of strings. Recent research in string theory and quantum gravity has forged a remarkable connection between quantum entanglement and the geometry of spacetime. The idea, first articulated by Mark van Romstonk, is that the fabric of spacetime is literally stitched together by quantum entanglement between the microscopic degrees of freedom of the theory. If the entanglement between two regions is reduced, the regions move farther apart in the emergent geometry. If the entanglement is completely removed, the space-time tears apart. This picture is supported by calculations in the AD-SCFT correspondence, where the entanglement entropy of a region in the boundary field theory can be computed by a geometric formula involving the area of a minimal surface in the gravitational bulk. The connection between entanglement and geometry has been formalized in the Ryu-Takayanagi formula and its generalizations, which have become central tools in modern theoretical physics. The implication is startling. Gravity, geometry, and the very structure of space and time may be consequences of quantum information, a perspective that has opened an entirely new frontier in the quest to understand the nature of reality at its deepest level. This view links string theory to cutting-edge ideas in quantum information. The discovery that spacetime geometry may emerge from quantum entanglement has forged a deep and unexpected connection between string theory and the burgeoning field of quantum information science. Concepts that were once the exclusive domain of computer science and quantum computing, such as entanglement entropy, quantum error correction, and computational complexity, have turned out to be directly relevant to the physics of black holes and the structure of spacetime. The Ryu-Takayanagi formula, which relates the entanglement entropy of a boundary region to the area of a minimal surface in the bulk, has become a bridge between these two disciplines. Even more remarkably, recent work has suggested that the interior of a black hole may be related to the computational complexity of the corresponding quantum state on the boundary. This connection, known as the complexity equals volume or complexity equals action conjecture, implies that the growth of the black hole interior is a manifestation of increasing quantum complexity. These ideas have attracted researchers from both the string theory and quantum information communities, creating a vibrant interdisciplinary frontier where the tools and concepts of one field illuminate the deepest questions of the other. Entanglement patterns may literally weave the geometry of the universe. The idea that entanglement weaves the fabric of spacetime is one of the most beautiful and provocative proposals in modern physics. In the AD-SCFT correspondence, two distant regions of the boundary field theory that are highly entangled with each other are connected by a short path through the bulk spacetime. If the entanglement between them is reduced, the connecting path becomes longer, and eventually, if the entanglement is completely removed, the spacetime between them pinches off entirely. This picture suggests that the geometry of the universe is not a pre-existing container for physics, but a structure that is actively constructed by the pattern of quantum correlations among its microscopic constituents. The idea has been made precise through tensor network models, which are mathematical structures used in quantum information science to represent many-body quantum states. In these models, the geometry of the network directly reflects the entanglement structure of the state, providing a concrete toy model for how spacetime geometry could emerge from quantum information. While these ideas are still being developed and many important questions remain open, they point towards a future in which the geometry of the universe is understood as an expression of its deepest quantum relationships. String theory also predicts fields called moduli tied to the shapes of hidden dimensions. When the extra dimensions of string theory are compactified into tiny shapes, the detailed geometry of those shapes determines the physical properties of the four-dimensional world we observe. But the geometry of the compact dimensions is not fixed. It can deform and change, and the parameters that describe these deformations give rise to scalar fields in the four-dimensional theory known as moduli. Each modulus corresponds to a particular way of deforming the compact space, such as changing its overall size, altering the ratio of its different radii, or twisting it in a specific manner. In the simplest versions of compactification, the moduli are massless fields that can take any value, meaning that the geometry of the extra dimensions is not uniquely determined, but can vary freely. This leads to a host of physical problems, because the values of the moduli determine fundamental constants, such as particle masses and coupling strengths. If the moduli are free to change, these constants would vary from one place to another in the universe, contradicting observations. Stabilizing the moduli, giving them a mass, and fixing their values has therefore become one of the central challenges of string phenomenology. These moduli could shift the fundamental constants of nature. The values of the moduli fields in string theory are not merely abstract mathematical parameters. They have direct physical consequences because they determine the sizes and shapes of the extra dimensions, which in turn control the masses of particles, the strengths of forces, and other fundamental constants of nature. If a modulus field were to shift even slightly, the electron mass might change, the strength of gravity might differ, or the strong nuclear force might behave differently. In a universe where the moduli are unstabilized, these constants would not be truly constant. They could vary slowly in time or differ from one region of the universe to another. This sensitivity of the fundamental constants to the geometry of the extra dimensions is both a feature and a challenge of string theory. On one hand, it offers a tantalizing explanation for why the constants of nature take the values they do. On the other hand, it raises the urgent question of why the moduli are fixed at the particular values that produce the physics we observe. The resolution of this question is intimately connected to the problem of vacuum selection and the structure of the string landscape. Stabilizing them has been one of the great challenges in the theory. The problem of moduli stabilization has occupied string theorists for decades and has spawned some of the most important technical developments in the field. In the simplest compactifications, the moduli are exactly massless, meaning there is no energy cost to changing the shape of the extra dimensions. This is a disaster for phenomenology because it implies the existence of long-range forces mediated by the moduli fields, which have never been observed. To stabilize the moduli, physicists have introduced a variety of mechanisms, including the effects of quantum fluxes threading through the compact dimensions, non-perturbative effects from branes wrapping around cycles in the compact space, and corrections arising from higher-order terms in the string theory expansion. The most influential construction is the KKLT scenario, proposed by Kakru, Kalash, Lind, and Trivedi, which combines these ingredients to produce a vacuum where all moduli are stabilized with a small positive cosmological constant. While the KKLT scenario is technically complex and not without controversy, it demonstrated that moduli stabilization is possible in principle within string theory and opened the door to constructing realistic string vacua. The number of possible Calabi-Yau shapes is staggeringly large. The Calabi-Yau manifolds that serve as the internal geometry of string compactifications come in an extraordinary variety of shapes and topologies. Mathematicians have catalogued tens of thousands of distinct Calabi-Yau threefolds, and the true number is believed to be vastly larger. Each Calabi-Yau manifold is characterized by its topology, the number of holes and handles it possesses, and by the values of various continuous parameters that describe its size and shape. Different topologies give rise to different numbers of particle generations, different gauge symmetry groups, and different patterns of Yukawa couplings. Even within a single topological class, the continuous parameters known as moduli can take different values, each producing a slightly different version of four-dimensional physics. When the effects of fluxes and branes are included, the number of distinct string vacua grows to an almost incomprehensible figure, estimated by some to be of the order of 10 to the power of 500. This enormous multiplicity is both a blessing and a curse. It makes it plausible that at least one vacuum matches our universe, but it also makes it extraordinarily difficult to identify which one. Each shape may produce a completely different universe with unique laws of physics. The physical properties of a universe compactified on a particular Calabi-Yau manifold depend sensitively on the detailed geometry of that manifold. The number of generations of quarks and leptons, the masses of particles, the strengths of forces, and even the cosmological constant are all determined, at least in principle, by the shape of the extra dimensions. Two compactifications that differ only slightly in their internal geometry can produce dramatically different low-energy physics. In one, there might be 3 generations of fermions, as in our universe. In another, there might be 5 or 17 or none. The gauge symmetry group might be the standard model in one case and something entirely different in another. This extraordinary sensitivity of the observable world to the microscopic geometry of the extra dimensions is one of the most striking features of string theory. It means that the laws of physics we observe are not the only possible laws. They are the laws that correspond to one particular choice of compactification geometry among a vast number of alternatives. This enormous diversity is known as the string landscape. The string landscape is the name given to the vast collection of possible string theory vacua, each corresponding to a different compactification geometry, a different configuration of fluxes and branes, and a different set of low-energy physical laws. The landscape metaphor evokes a mountainous terrain with an enormous number of valleys, each valley representing a stable or metastable vacuum with its own particular values of the fundamental constants. The existence of the landscape was first appreciated in the early 2000s, when it became clear that the mechanisms for moduli stabilization could generate an astronomically large number of distinct vacua. The landscape has been the subject of intense debate within the physics community. Supporters argue that it provides a natural framework for understanding the apparent fine-tuning of the constants of nature, particularly the cosmological constant. Critics argue that a theory with so many possible solutions is essentially unpredictive, since it can accommodate almost any set of observations. The landscape has become one of the most polarizing concepts in modern theoretical physics, forcing physicists to confront fundamental questions about the nature of scientific prediction and explanation. The landscape might contain more possible universes than atoms in the observable cosmos. Estimates of the number of vacua in the string landscape vary, but the most commonly cited figure is of the order of 10 to the power of 500. To put this number in perspective, the observable universe contains roughly 10 to the power of 80 atoms. The number of string vacua exceeds the number of atoms by a factor so immense that it defies all ordinary intuition. Each of these vacua represents a self-consistent universe with its own particular values of particle masses, force strengths, and cosmological parameters. The sheer size of the landscape has led some physicists to argue that it is futile to search for a unique vacuum that matches our universe, and that instead, one should seek statistical or environmental explanations for the observed values of the fundamental constants. Others have taken the landscape as motivation to develop new selection principles, computational algorithms, or symmetry arguments that might narrow the search. The landscape has also sparked interest in machine learning and data science techniques as tools for exploring and classifying the enormous space of possibilities. Whatever the eventual resolution, the staggering size of the string landscape has permanently changed the way physicists think about the relationship between fundamental theory and observable reality. Each valley of the landscape corresponds to a different set of physical constants. In the landscape metaphor, Each valley represents a local minimum of the potential energy function that governs the moduli fields. A universe sitting in a particular valley will have moduli fields that are stabilized at specific values, and these values determine the fundamental constants of that universe. The depth of the valley corresponds to the vacuum energy or cosmological constant of that universe. Wide, shallow valleys correspond to universes with large extra dimensions and weak gravity, while narrow, deep valleys might correspond to universes with small extra dimensions and strong gravity. The barriers between neighboring valleys determine how stable each vacuum is, since a universe in one valley could, in principle, tunnel through a barrier to reach a neighboring valley with lower energy. This quantum tunneling process would cause a catastrophic phase transition, fundamentally altering the laws of physics. The landscape picture suggests that our universe occupies one particular valley among an enormous number of possibilities, and that the specific physical constants we observe are a consequence of the particular vacuum in which we find ourselves, rather than being uniquely determined by an underlying principle. Some physicists link this to the idea of the multiverse. The string landscape naturally leads to the concept of a multiverse, a vast collection of physically realized universes, each occupying a different valley of the landscape and each governed by a different set of physical laws. In the context of eternal inflation, the dominant cosmological framework, the universe is constantly spawning new regions of space, each of which can settle into a different vacuum of the landscape. This process creates an ever-expanding mosaic of bubble universes, each with its own particle content, coupling constants, and cosmological parameters. Our observable universe would be just one such bubble, a tiny patch in an incomprehensibly vast multiverse. The multiverse idea is appealing because it offers a potential explanation for the apparent fine-tuning of the physical constants, including the famously tiny cosmological constant. If there are enough universes sampling enough vacua, then at least some will have constants compatible with the existence of galaxies, stars, and life. The multiverse is also deeply controversial because it challenges traditional notions of scientific prediction and falsifiability. Nonetheless, many leading string theorists regard the multiverse as a natural consequence of the landscape and take it seriously as a framework for understanding our universe. Our universe may be one bubble among countless possibilities predicted by string theory. In the multiverse picture inspired by the string landscape, our universe is a single bubble of space-time embedded within an eternally inflating cosmic ocean. Each bubble is a self-contained universe with its own dimensionality, particle spectrum, and physical laws, determined by the particular vacuum of the landscape in which it formed. The boundaries between bubbles are regions of enormously high energy, and collisions between bubbles, though exceedingly rare in most models, could in principle leave observable imprints on the cosmic microwave background. Cosmologists have searched for such signals, looking for disc-shaped anomalies or cold spots that might indicate a past collision with a neighboring bubble universe. So far, no convincing evidence has been found, but the search continues as observational techniques improve. The bubble universe picture is a dramatic expansion of our conception of reality. It suggests that the cosmos is far larger and far more varied than the observable universe we can see, and that the particular physical laws we experience may be no more fundamental than the particular weather we happen to encounter on a given day. This perspective, whether ultimately confirmed or not, has profoundly influenced the way physicists think about the relationship between theory and observation. Critics argue this makes the theory nearly impossible to test. One of the most common and pointed criticisms of string theory is that it has not produced a single unique, falsifiable prediction that could be tested by experiment. The existence of the string landscape, with its enormous number of possible vacua, makes it difficult to derive specific predictions for the values of the fundamental constants, since almost any set of values can be accommodated somewhere in the landscape. Critics, including prominent physicists such as Lee Smolin and Peter Woit, have argued that a theory that can explain everything effectively explains nothing. They contend that string theory has become detached from the traditional scientific method, which requires that theories make concrete predictions that can be confirmed or refuted by observation. The lack of direct experimental evidence, despite decades of effort, has fueled a broader debate about the nature of scientific progress and the standards by which theoretical frameworks should be judged. Defenders of string theory respond that the theory has made many indirect contributions and that the absence of direct evidence reflects the extreme energy scales at which string effects become important, far beyond the reach of any foreseeable experiment. The debate continues to be one of the most vigorous and consequential in contemporary physics. But supporters note it may explain why our universe is tuned for life. The apparent fine-tuning of the physical constants for the existence of life has long been one of the deepest puzzles in physics. The cosmological constant, for example, is observed to be extraordinarily small and positive, a value that seems to require an improbable cancellation among much larger contributions. The masses of quarks and the strength of the nuclear forces are similarly finely balanced. If any of these constants differed by even a small amount, stars would not form, atoms would not be stable, and life as we know it would be impossible. The string landscape offers a potential explanation for this tuning. If there are an enormous number of vacua with different values of the constants, then it is not surprising that at least some of them are compatible with life. In those vacua, observers like us can exist and ask why the constants have the values they do. This reasoning, known as the anthropic principle, remains controversial. Many physicists regard it as a retreat from the goal of finding a unique explanation for the constants of nature. Others see it as a pragmatic and perhaps necessary response to the reality of the landscape. String theory has also reshaped pure mathematics. The influence of string theory on pure mathematics has been nothing short of extraordinary. Over the past 4 decades, ideas and techniques originating in string theory have led to major breakthroughs in algebraic geometry, differential geometry, topology, and number theory. The relationship between physics and mathematics has always been productive, but string theory has taken this cross-pollination to an entirely new level. Concepts such as mirror symmetry, topological string theory, and the Witten genus have opened up new branches of mathematical research that would not have existed without the inspiration of string theory. Mirror symmetry, for instance, revealed a deep and unexpected duality between pairs of Calabi-Yau manifolds, allowing mathematicians to solve problems in enumerative geometry that had been open for over a century. The influence has flowed in both directions, with advances in mathematics feeding back into the development of string theory and deepening our understanding of its structure. The mathematical legacy of string theory is secure regardless of its ultimate status as a physical theory, because the mathematical truths it has revealed are permanent contributions to human knowledge. It has solved problems in geometry, topology, and even number theory. String theory has provided solutions to mathematical problems that had resisted all conventional approaches. In enumerative geometry, mirror symmetry allowed physicists to count the number of rational curves on a Calabi-Yau manifold, yielding results that astonished mathematicians and were later confirmed by rigorous mathematical proof. In topology, the Witten invariance of 3 manifolds, derived from topological quantum field theories inspired by string theory, opened entirely new avenues of research. In number theory, the connection between modular forms and string amplitudes has revealed deep relationships between objects that had seemed entirely unrelated. Black hole entropy calculations have led to new results in combinatorics and the theory of partitions. The mathematical output of string theory has been so prolific that it has led to the creation of new subfields, including homological mirror symmetry, derived categories in string theory, and the mathematics of D-branes. These contributions have earned Fields medals and other major mathematical awards for researchers working at the interface of physics and mathematics. The extraordinary fertility of string theory as a source of mathematical ideas is one of its most undeniable achievements. Entire fields of maths have advanced through questions raised by string theory. Beyond solving individual problems, string theory has stimulated the development of entire fields of mathematics. Homological mirror symmetry, proposed by Maxim Kontsevich, grew directly out of the mirror symmetry discovered by string theorists and has become one of the most active areas of research in modern mathematics. The study of derived categories and their role in D-brane physics has transformed algebraic geometry. Topological string theory has inspired new approaches to knot invariance and the topology of three manifolds. The mathematical structure of conformal field theory, which underlies the worldsheet description of strings, has led to profound advances in the representation theory of infinite-dimensional algebras. Even the study of moduli spaces, which is central to both algebraic geometry and string compactification, has been enriched by physical insights. The questions that string theory poses are often qualitatively different from those that mathematicians would naturally ask, and this fresh perspective has been a powerful engine for mathematical discovery. The relationship between string theory and mathematics is now so deep and so productive that it is difficult to imagine either field developing in isolation. Mathematicians and physicists now collaborate in unprecedented ways. The interaction between string theorists and mathematicians has become one of the most productive interdisciplinary collaborations in the history of science. Conferences, workshops, and research centers devoted to the interface of mathematics and string theory have sprung up around the world. Mathematicians attend lectures by string theorists to learn about new conjectures and physical insights, while physicists study advanced mathematics to deepen their understanding of the theory. This collaboration has produced a remarkable body of work that belongs equally to both disciplines. The Fields Medal awarded to Edward Witten, a theoretical physicist, is perhaps the most visible symbol of this interdisciplinary marriage. Joint research programs have tackled problems ranging from the geometry of Calabi-Yau manifolds to the mathematical foundations of quantum field theory. The collaboration has also influenced the training of young researchers, with graduate students increasingly expected to be fluent in both the language of physics and the rigor of mathematics. The partnership between these two communities, driven by the shared challenge of understanding string theory, has produced insights that neither could have achieved alone. String theory also influenced studies of superconductors and exotic materials. One of the most surprising applications of string theory has been in condensed matter physics, the study of how atoms and electrons organize themselves into materials with exotic properties. High-temperature superconductors, strange metals, and quantum spin liquids are systems where the electrons interact so strongly that conventional theoretical methods fail. The AD-SCFT correspondence, originally developed in the context of string theory and quantum gravity, has provided a new set of tools for studying these strongly interacting systems. By mapping a condensed matter problem onto a gravitational problem in a higher dimensional space, physicists can perform calculations that would be impossible using traditional techniques. This approach, known as holographic condensed matter or AD-SCMT, has yielded insights into the phase diagrams of strongly correlated materials, the behavior of strange metals, and the transport properties of quantum critical systems. While the holographic models are not exact descriptions of real materials, they capture universal features that are shared by many strongly interacting systems, providing qualitative and sometimes semi-quantitative understanding of phenomena that were previously beyond the reach of theory. Through holography, it has provided tools to explore strongly interacting systems. The holographic approach to strongly interacting systems has become a thriving subfield at the intersection of string theory and condensed matter physics. The basic idea is that a strongly coupled quantum system in a certain number of dimensions can be described by a weakly curved gravitational theory in one higher dimension. Calculations that are intractable in the original strongly coupled theory become straightforward in the gravitational dual. This technique has been applied to a wide range of problems, from the viscosity of the quark-gluon plasma to the conductivity of strange metals and the entanglement properties of quantum many-body systems. One of the most celebrated results is the calculation of the ratio of shear viscosity to entropy density for a strongly coupled fluid, which was found to satisfy a universal lower bound. This bound, derived from the gravitational dual, has been compared with experimental data from heavy ion collisions at the relativistic heavy ion collider and the Large Hadron Collider, and the agreement is remarkably close. The holographic toolkit continues to grow, with new gravitational solutions being constructed to model an ever wider range of condensed matter phenomena. Even the physics of quark-gluon plasmas has been studied with string-inspired methods. The quark-gluon plasma is a state of matter in which quarks and gluons, normally confined inside protons and neutrons, roam freely in a hot, dense soup. This exotic state existed in the first microseconds after the Big Bang and has been recreated in heavy ion collision experiments at facilities such as the relativistic heavy ion collider and the Large Hadron Collider. The quark-gluon plasma is an extremely strongly coupled system, meaning that its constituents interact with each other so intensely that perturbative methods, the standard calculational tools of quantum chromodynamics, simply do not work. String theory has provided an alternative approach. Using the AD-SCFT correspondence, physicists have modeled the quark-gluon plasma as a fluid in a gravitational theory, calculating its viscosity, diffusion constants, and energy loss rates. The result, that the ratio of shear viscosity to entropy density is very close to the holographic lower bound, has been one of the most widely discussed applications of string theory to real-world physics. While the holographic models are not exact, they capture essential features of the strongly coupled plasma and have guided the interpretation of experimental data in ways that no other theoretical framework could. The theory links phenomena across scales, from black holes to laboratory materials. One of the most astonishing features of string theory and its holographic offspring is the ability to connect physical phenomena at vastly different scales within a single mathematical framework. The same duality that describes the quantum microstates of a black hole can also shed light on the conductivity of a strange metal in a condensed matter laboratory. The same equations that govern gravitational waves in a curved spacetime can inform our understanding of energy transport in a strongly coupled quantum fluid. This universality is not accidental. It reflects the deep structural similarities between strongly interacting systems at different scales, similarities that are most naturally revealed through the lens of holographic duality. The cross-scale connections forged by string theory have led to new collaborations between physicists working in traditionally separate fields, from astrophysics and cosmology to nuclear physics and materials science. While each application has its own specific context and limitations, the overarching theme is one of unity. String theory, even if not yet confirmed as the fundamental theory of nature, has provided a mathematical language that reveals hidden connections across the entire spectrum of physical phenomena. Despite its elegance, string theory has yet to make direct experimental predictions. For all its mathematical beauty and conceptual depth, string theory faces a stubborn practical problem. It has not yet produced a clear, unambiguous prediction that can be tested in a laboratory or observatory. The fundamental reason is one of scale. The characteristic energy at which stringy effects become visible is the Planck energy, which is roughly a quadrillion times higher than the energies accessible at the Large Hadron Collider. At currently accessible energies, the differences between string theory and a conventional quantum field theory are expected to be immeasurably small. This vast gulf between the predictions of the theory and the capabilities of existing experiments has made direct testing extraordinarily difficult. Some physicists argue that the inability to test string theory is a temporary technological limitation that may be overcome in the future, perhaps through cosmological observations or gravitational wave astronomy. Others contend that a theory that cannot be tested even in principle at accessible energies should be held to different standards of scrutiny. The debate over the testability of string theory is not merely a technical question, but touches on fundamental issues in the philosophy of science, including what it means for a theory to be scientific. Supersymmetric partners have not appeared in the Large Hadron Collider. The Large Hadron Collider, the most powerful particle accelerator ever constructed, was widely expected to discover supersymmetric particles if they existed at the energy scales predicted by the most natural versions of string theory. After years of operation and the collection of enormous quantities of data, no supersymmetric partners have been found. This null result has had a significant impact on the string theory community, forcing theorists to reconsider the energy scales at which supersymmetry might be broken, and to explore less natural versions of the theory in which the supersymmetric partners are heavier than initially expected. The absence of supersymmetry at the LHC does not rule out string theory, because the theory is flexible enough to accommodate supersymmetry breaking at arbitrarily high energies. However, it does weaken one of the strongest motivations for believing that string theory would soon be experimentally confirmed. The LHC continues to take data and to search for subtle signals of new physics, and future upgrades may extend its reach. But for now, the non-discovery of supersymmetric particles remains one of the most sobering developments in the field. No evidence of extra dimensions has been found so far. Another key prediction of string theory, the existence of extraspatial dimensions beyond the three we experience, has also remained experimentally unconfirmed. If the extra dimensions were large enough, or if gravity leaked into them in detectable ways, experiments at the LHC or precision tests of gravity at short distances might reveal their presence. Searches have been conducted for signatures such as missing energy events in particle collisions, deviations from Newton's inverse square law at submillimeter scales, and the production of Kaluza-Klein excitations, heavier copies of known particles associated with motion in the extra dimensions. None of these signatures have been observed. The extra dimensions, if they exist, must be either very small, very well hidden, or accessible only at energies far beyond current reach. Some models, such as the large extra dimension scenario proposed by Arkani-Hamed, Dimopoulos and Diwali, or the warped extra dimensions model of Randall and Sundram, make specific predictions that are within the range of current experiments, and the failure to detect these predictions constrains the allowed parameter space of these models. The search for extra dimensions continues through gravitational wave observations and precision cosmological measurements. This absence of data has led to criticism of the theory. The lack of experimental confirmation has fueled a vigorous and sometimes bitter debate about the status of string theory as a scientific enterprise. Critics argue that after more than 4 decades of development, the theory should have produced at least one concrete prediction that can be tested and potentially falsified. The failure to discover supersymmetric particles, extra dimensions, or any other signature uniquely predicted by string theory has led some physicists to question whether the theory is on the right track at all. Books and articles critical of string theory have appeared, arguing that the field has consumed a disproportionate share of resources and talent without delivering on its promises. Defenders respond that string theory has produced deep insights into the nature of gravity, black holes, and quantum field theory, and that the absence of direct experimental evidence is a consequence of the extreme energy scales involved rather than a fundamental flaw in the theory. They also point out that many of the greatest advances in theoretical physics, from general relativity to quantum mechanics, required decades before their predictions could be fully tested. The debate remains unresolved and continues to shape the direction of fundamental physics research. Yet indirect clues may still emerge from cosmology. While direct detection of strings or extra dimensions remains beyond current technological capabilities, cosmology offers a promising window into string-scale physics. The very early universe was a laboratory of extreme energies, and the imprints of those early moments are encoded in the cosmic microwave background radiation, the distribution of galaxies, and the spectrum of primordial gravitational waves. String theory makes specific predictions about the nature of cosmic inflation, the rapid expansion that occurred in the first fraction of a second after the Big Bang. Different string theory models of inflation predict different patterns of temperature fluctuations in the cosmic microwave background, different ratios of scalar to tensor perturbations, and different signatures of non-Gaussianity. Current and future observatories, including space-based gravitational wave detectors and next-generation cosmic microwave background telescopes, may have the sensitivity to distinguish between these predictions. If a particular pattern of cosmological observations were found to match a specific string theory model, it would provide powerful circumstantial evidence in favor of the theory, even if the strings themselves could never be directly observed. Primordial gravitational waves could carry the fingerprints of string theory. Gravitational waves, ripples in the fabric of spacetime predicted by general relativity and first directly detected in 2015, offer a unique probe of physics at the highest energy scales. Primordial gravitational waves, generated during the inflationary epoch in the first moments of the universe, carry information about the energy scale of inflation and the physics of the very early cosmos. String theory models of inflation make predictions for the amplitude and spectrum of these primordial waves. Some models predict a detectable signal, while others predict waves too faint to observe with current technology. The detection protocols for primordial gravitational waves typically focus on a characteristic pattern called B-mode polarization in the cosmic microwave background, which would be imprinted by the gravitational waves as they propagated through the early universe. Future space-based gravitational wave observatories may also be sensitive to a stochastic background of primordial waves at much lower frequencies. If the characteristics of the detected gravitational waves matched the predictions of a particular string inflation model, it would provide one of the first observational connections between string theory and the physical universe, a milestone that the entire field eagerly awaits. Hypothetical objects, called cosmic strings, may also stretch across the universe. Cosmic strings are one-dimensional topological defects that could have formed during phase transitions in the very early universe. In certain string theory models, fundamental strings or D-strings produced during cosmological events, such as brane collisions, could be stretched to astronomical scales by the expansion of the universe, becoming cosmic-sized strings that span vast distances across the cosmos. These cosmic strings, if they exist, would produce a variety of observable effects, including gravitational lensing of distant galaxies, characteristic patterns in the cosmic microwave background, and a distinctive spectrum of gravitational wave emission. Searches for cosmic strings have been conducted using data from the cosmic microwave background, pulsar timing arrays, and gravitational wave detectors, but no convincing detection has been made so far. The non-detection places upper limits on the tension of cosmic strings, constraining the models that predict them. However, the allowed parameter space is still large, and future observations may yet reveal their presence. The discovery of cosmic strings would be a remarkable event, providing direct evidence for physics at energy scales far beyond the reach of any particle accelerator, and potentially confirming a key prediction of string theory. These relics, if found, would be striking evidence for the theory. The detection of any cosmological relic predicted by string theory, whether cosmic strings, primordial gravitational waves with a specific spectrum, or signatures of extra dimensions in the cosmic microwave background, would dramatically change the status of the theory. It would move string theory from the realm of pure mathematical speculation into the domain of empirically supported science. The nature of the evidence would likely be statistical and indirect, rather than a direct observation of a vibrating string. But that is the norm in cosmology and particle physics, where theories are tested through their predictions for observable distributions and correlations. A detection would also help narrow down the vast landscape of possible string vacua, since only certain vacua produce the kinds of cosmological relics that could be observed. Conversely, the continued absence of any cosmological signature would further tighten the constraints on the theory and could eventually push viable string models into a corner where their predictions are forever beyond observational reach. The coming decades of cosmological observation will be critical, offering perhaps the best near-term opportunity to subject string theory to the test of empirical evidence. Some versions predict that tiny black holes could form at high energies. In certain scenarios with large or warped extra dimensions, the effective strength of gravity at short distances could be much greater than we observe in our everyday experience. If this is the case, the energy required to create a black hole could be much lower than the Planck energy, potentially bringing it within the reach of particle colliders or ultra-high-energy cosmic ray interactions. These hypothetical microscopic black holes would be utterly unlike their astrophysical counterparts. They would be subatomic in size, would exist for only an unimaginably brief instant, and would evaporate almost immediately through Hawking radiation, producing a burst of particles that could be detected. The Large Hadron Collider searched for signatures of microscopic black hole production, such as events with an unusually large number of high-energy particles, but found nothing. This null result constrains the extra-dimension models that predict low-energy black hole formation, but does not rule out string theory as a whole. The prospect of creating and studying microscopic black holes remains one of the most dramatic predictions associated with string theory, and if it were ever achieved, It would provide direct experimental access to the physics of quantum gravity. Detecting them would reveal quantum gravity directly. The detection of microscopic black holes would be a watershed moment in the history of physics, providing the first direct experimental window into the realm of quantum gravity. Currently, quantum gravitational effects are expected to become important only at the Planck scale, an energy roughly 1,000,000 billion times higher than what the Large Hadron Collider can achieve. If extra dimensions lowered this threshold, microscopic black holes produced in collisions would evaporate through Hawking radiation, and the spectrum of emitted particles would encode information about the quantum gravitational physics of the evaporation process. By studying the energy distribution, particle types, and angular correlations of the radiation, physicists could probe the Hawking temperature, the number of extra dimensions, and the detailed dynamics of the evaporation. This would test some of the most celebrated predictions of theoretical physics, predictions that have remained purely theoretical since Hawking's original calculation in the 1970s. The detection would also constrain or confirm specific string theory models, since different compactification schemes predict different black hole production rates and decay signatures. While the non-observation at the LHC has made this scenario less likely, it remains a tantalizing possibility for future experiments at higher energies. String theory remains the most mathematically complete approach to unifying physics. Despite the absence of direct experimental confirmation, string theory remains the most developed and mathematically rigorous attempt to unify all the forces of nature, including gravity, within a single quantum framework. No other approach to quantum gravity has achieved the same combination of internal consistency, mathematical depth, and breadth of application. Loop quantum gravity, the main alternative, has made important progress in quantizing the geometry of spacetime, but has not yet achieved the same level of success in incorporating matter and the other forces of nature. Causal set theory, asymptotic safety, and other approaches each address aspects of the quantum gravity problem, but lack the comprehensive scope of string theory. String theory provides a consistent framework for quantum gravity, a microscopic explanation of black hole entropy, a holographic duality connecting gravity to quantum field theory, and a rich mathematical structure that has inspired breakthroughs in pure mathematics. These achievements, taken together, represent a body of work unmatched by any competing approach. Whether string theory is ultimately the correct description of nature remains to be seen, but its role as the leading candidate for a unified theory of physics is firmly established. It has drawn countless students into physics and mathematics. The intellectual allure of string theory has attracted generations of some of the brightest students into theoretical physics and mathematics. The promise of a unified theory of everything, the mathematical elegance of the framework, and the sheer ambition of the program have drawn young researchers from around the world into a field that demands the highest levels of mathematical sophistication and physical intuition. Many of these students have gone on to make significant contributions not only to string theory itself, but to adjacent fields such as cosmology, condensed matter physics, quantum information, and pure mathematics. The training provided by a deep engagement with string theory, including mastery of advanced differential geometry, algebraic topology, quantum field theory, and general relativity, equips students with a uniquely versatile skill set. Even those who eventually move away from string theory into other areas of physics or mathematics carry with them the tools and perspectives gained from their studies. The cultural impact of string theory on the scientific community has been profound, shaping the intellectual landscape of an entire era and inspiring a level of interdisciplinary collaboration that is rare in the history of science. Even if string theory is not the final answer, it has transformed our understanding of space and time. Regardless of whether string theory turns out to be the ultimate description of nature, its contributions to our understanding of fundamental physics are beyond dispute. It has revealed that space-time may not be fundamental but emergent, that extra dimensions of space may exist beyond the three we perceive, and that the notion of a point particle may be an approximation of a deeper, extended structure. It has provided the first microscopic account of black hole entropy, demonstrated the holographic nature of gravity, and established deep connections between quantum information and the geometry of space-time. These insights have permanently altered the conceptual landscape of theoretical physics, and they will not be undone even if a different framework ultimately proves to be the correct theory of nature. The history of physics is full of examples where a theory that was not the final answer nonetheless provided essential building blocks for the theory that followed. Newtonian mechanics, while superseded by general relativity, remains an indispensable approximation. In much the same way, string theory may prove to be an indispensable stepping stone on the path to the ultimate theory, even if it is not that theory itself. It has revealed deep connections between seemingly unrelated areas of physics. One of the most enduring legacies of string theory is the web of unexpected connections it has uncovered between areas of physics that were previously thought to be entirely separate. The AD-SCFT correspondence connects gravity to quantum field theory. Holographic duality links black hole physics to condensed matter systems. Mirror symmetry in string compactification has led to breakthroughs in algebraic geometry. The study of D-branes has influenced our understanding of gauge theories. The mathematical structure of scattering amplitudes, developed in the context of string theory, has led to revolutionary new methods for calculating particle interactions in quantum chromodynamics. These connections are not superficial analogies. They are precise mathematical equivalences that reveal deep structural relationships between different physical phenomena. The picture that emerges is one of a tightly interconnected web, in which the fundamental laws of nature are far more unified than they appear from any single vantage point. String theory has taught us that the apparent diversity of physical phenomena may mask a deeper unity, a lesson that will continue to guide theoretical physics regardless of the ultimate fate of the theory. It has shown that gravity and quantum mechanics need not be enemies, but partners. For most of the 20th century, gravity and quantum mechanics appeared to be fundamentally incompatible. General relativity describes gravity as the curvature of a smooth, continuous spacetime, while quantum mechanics describes the other forces in terms of discrete, probabilistic events. Every attempt to quantize gravity using the standard methods of quantum field theory produced meaningless infinities that could not be removed. String theory resolved this clash by replacing point particles with extended strings, whose smooth, spread-out nature tames the violent short-distance behavior that causes the infinities. In string theory, gravity and quantum mechanics coexist peacefully, each enriching the other. The graviton, the quantum carrier of gravity, arises naturally as a vibrational mode of the string, and its interactions are automatically finite and well-defined. The holographic principle and the AD-SCFT correspondence have taken this reconciliation even further, showing that a gravitational theory and a quantum field theory can be two descriptions of exactly the same physics. String theory has demonstrated that the tension between gravity and quantum mechanics was not a fundamental obstacle, but a sign that both needed to be embedded in a larger framework. It has made us rethink what is meant by dimensions and particles. Before string theory, Dimensions were simple, unambiguous features of the physical world, 3 of space and 1 of time, and particles were point-like objects characterized by their mass, charge, and spin. String theory has profoundly complicated both of these notions. Dimensions may be more numerous than we perceive, compactified into tiny shapes that determine the properties of the visible world. The very concept of dimensionality becomes ambiguous at the shortest distances, where T-duality shows that a large dimension and a small one can be physically equivalent. Particles, meanwhile, are no longer fundamental point-like objects, but vibrational modes of extended strings, with their properties determined by the pattern and frequency of vibration. What we call an electron or a quark is, in the string theory picture, a particular way in which a string vibrates. Different vibrational modes give rise to different particles, much as different modes of vibration of a musical string produce different notes. This reimagining of the basic building blocks of reality is one of the most intellectually daring aspects of string theory, challenging us to abandon familiar concepts and embrace a radically new picture of the physical world. It has expanded the very idea of what a universe can be. String theory has vastly enlarged our conception of the possible. Before string theory, the universe was assumed to have a fixed set of laws determined by a unique fundamental theory. String theory suggests instead that there may be an enormous number of possible universes, each with its own laws, its own particle content, and its own values of the fundamental constants. The string landscape, with its estimated 10 to the power of 500 vacua, dwarfs anything previously contemplated in physics. The multiverse, if it exists, makes our observable universe a single bubble in an incomprehensibly vast cosmic ocean. Even the notion of spacetime itself has been expanded, with extra dimensions, branes, and holographic surfaces adding layers of structure that were entirely unanticipated. String theory has taught us that the universe is stranger, richer, and more varied than the most imaginative science fiction. Whether the multiverse is real or the extra dimensions are ever detected, the sheer scope of the possibilities revealed by string theory has permanently expanded the horizons of human thought about the cosmos and our place within it. The smoothness of strings prevents the violent point-like collisions that cause infinities in other theories. In conventional quantum field theory, particles are treated as mathematical points with no spatial extent. When two-point particles interact, they come into contact at a single point in spacetime, and the energy density at that point can become infinite. These infinities, known as ultraviolet divergences, plague the quantum field theory of gravity and have resisted all attempts at removal through the standard technique of renormalization. String theory solves this problem in an elegantly simple way. Because strings have a finite length, they cannot collide at a single point. Instead, their interactions are spread out over a small but non-zero region of spacetime, smoothing out the dangerous singularities that would arise from point-like collisions. The extended nature of the string acts as a natural regulator, automatically taming the infinities that make quantum gravity so difficult in a point-particle framework. This smoothing effect is not imposed by hand, but arises naturally from the geometry of string interactions, making it one of the most compelling features of the theory. The finiteness of string theory, achieved without the need for any external cutoff or renormalization procedure, is a remarkable mathematical property that sets it apart from all other known approaches to quantum gravity. String theory suggests that what we call particles are shadows cast by vibrating strings in unseen dimensions. In string theory, the particles we detect in experiments are not fundamental objects in their own right, but projections of a higher dimensional reality onto our four-dimensional world. A string vibrating in 10 or 11 dimensions appears, from our limited four-dimensional perspective, as a particle with specific properties of mass, charge, and spin. The full richness of the string's behavior is invisible to us because we cannot perceive the extra dimensions in which it moves. What we call an electron is a particular pattern of vibration viewed from our restricted vantage point. What we call a photon is another. The diversity of the particle zoo, which seems so arbitrary and unexplained in the standard model, is revealed by string theory to be a consequence of the variety of vibrational modes available to a single type of fundamental object. In this picture, the particles are shadows, not in the sense of being unreal, but in the sense of being incomplete representations of a deeper, higher dimensional truth. The analogy is reminiscent of Plato's allegory of the cave, in which prisoners mistake the shadows on the wall for reality, unaware of the richer world that casts them. The Planck length is the smallest meaningful scale in physics, roughly where strings are thought to exist. The Planck length is an incredibly tiny distance, roughly 10 to the power of -35 meters, formed from the three fundamental constants of nature: the speed of light, Newton's gravitational constant, and the reduced Planck constant. It represents the scale at which quantum gravitational effects are expected to become dominant, and the classical notion of smooth, continuous spacetime is expected to break down. In string theory, the fundamental strings are believed to have a size comparable to the Planck length, making them far too small to be resolved by any conceivable experiment using current technology. To appreciate just how small the Planck length is, consider that if an atom were enlarged to the size of the observable universe, the Planck length would still be smaller than a grain of sand. At distances comparable to the Planck length, the familiar concepts of distance, area, and volume lose their ordinary meaning, and the geometry of spacetime becomes subject to violent quantum fluctuations. String theory provides a framework for describing physics at this extreme scale, replacing the point-like singularities of quantum field theory with smooth, extended objects whose behavior is well-defined even at the Planck length. Mirror symmetry, discovered through string theory, became an entire field of mathematical study. Mirror symmetry is one of the most beautiful and surprising mathematical discoveries to emerge from string theory. It was first noticed in the late 1980s when physicists realized that two Calabi-Yau manifolds with very different geometric properties could give rise to exactly the same four-dimensional physics when used as compactification spaces in string theory. The two manifolds are called mirror partners, and the relationship between them, known as mirror symmetry, exchanges the roles of two types of geometric data, roughly speaking swapping the shape of holes with the shape of cycles. This mathematical duality turned out to have far-reaching implications for pure mathematics. It allowed physicists to calculate the number of rational curves on a Calabi-Yau manifold by performing a much simpler calculation on its mirror partner, producing results that had eluded mathematicians for decades. The discovery electrified the mathematical community and launched an entire field of research known as homological mirror symmetry, which was given a precise mathematical formulation by Maxim Kontsevich. Mirror symmetry remains one of the most active areas of research at the interface of physics and mathematics, and its continued development illustrates the extraordinary power of string theory as a source of mathematical insight. The anthropic principle may explain why our universe has the constants it does within the vast landscape. The anthropic principle, in the context of the string landscape, proposes that the values of the fundamental constants of nature are not determined by a unique theoretical principle, but are selected by the requirement that the universe must be compatible with the existence of observers. In a landscape of 10 to the power of 500 possible vacua, the vast majority will have physical constants that are wildly different from those of our universe. Most of these hypothetical universes would be inhospitable to life, lacking stable atoms, stars, or the complex chemistry necessary for biology. Only a tiny fraction of the vacua will have constants finely tuned enough to permit the existence of observers who can ask why the constants have the values they do. The anthropic principle suggests that we inevitably find ourselves in such a vacuum, simply because we could not exist in any other. This reasoning is deeply controversial. Critics argue that it amounts to giving up on the traditional goal of physics, which is to derive the constants of nature from first principles. Supporters respond that in a landscape of enormous diversity, the anthropic principle may be the only viable explanation for the observed fine-tuning. Strings carry patterns of vibration that encode the mass and charge of particles. The central insight of string theory is that the properties of elementary particles are not arbitrary inputs, but consequences of the vibrational state of a fundamental string. A string can vibrate in many different modes, and each mode corresponds to a different particle with different values of mass, charge, spin, and other quantum numbers. The frequency and pattern of vibration determine the mass of the particle, with higher frequency modes corresponding to heavier particles. The way the string moves through the extra dimensions determines its charge under the various gauge symmetries. Even the spin of a particle, which in conventional physics is a somewhat mysterious intrinsic property, arises naturally from the rotational motion of the vibrating string. This picture provides a unified explanation for the entire particle spectrum. Every particle in the standard model and every particle beyond it is simply a different note played by the same type of string. The elegance of this idea is one of the primary reasons string theory has attracted so many brilliant minds. It suggests that the apparent complexity of the particle zoo is an illusion, hiding a deeper simplicity in which all of physics is the music of vibrating strings. The bulk is the higher dimensional space in which our brain universe may float. In the brainworld scenarios of string theory, our observable universe is a three-dimensional brain embedded in a higher dimensional space known as the bulk. The bulk may contain additional brains, strings, and other objects that are invisible to us because the particles and forces of the standard model are confined to our brain. Only gravity, carried by closed strings that are free to propagate through the entire bulk, can move beyond the brain and probe the extra dimensions. The bulk could be vast, possibly infinite, and may contain other brain universes parallel to our own, each potentially hosting its own version of physics. The brainworld picture offers a natural explanation for the weakness of gravity compared to the other forces. If gravity can spread into the extra dimensions of the bulk, while the other forces are confined to our brain, then gravity would appear weaker on the brain simply because it is diluted across a larger space. This idea, central to the models of Randall and Sundram, has been extensively studied and has led to testable predictions for short-range gravitational experiments and particle collider searches. Wormholes and entanglement may be two sides of the same coin in string theory. One of the most provocative proposals in recent theoretical physics is the ER equals EPR conjecture, put forward by Juan Maldacena and Leonard Susskind. It proposes that wormholes, the Einstein-Rosen bridges that connect distant regions of space-time, and quantum entanglement, the Einstein-Podolsky-Rosen correlations between distant particles, are in fact two descriptions of the same underlying phenomenon. According to this conjecture, every pair of entangled particles is connected by a tiny, non-traversable wormhole, and every wormhole is a manifestation of entanglement between the degrees of freedom at its two ends. This idea connects two of the most iconic concepts in theoretical physics, one from general relativity and one from quantum mechanics, within the framework of string theory. The ER equals EPR conjecture has profound implications for our understanding of the black hole information paradox, the structure of space-time, and the relationship between quantum mechanics and gravity. While the conjecture remains unproven in full generality, it has inspired a great deal of productive research and has deepened the connection between quantum information and the geometry of space-time. String theory's ultimate legacy may be philosophical, reshaping how we imagine reality itself. Beyond its technical achievements, string theory has had a profound impact on the way humans think about the nature of reality. It has introduced the possibility that the universe has more dimensions than we can perceive, that the laws of physics may vary from one region of the cosmos to another, and that what we consider to be fundamental may be emergent. It has challenged the centuries-old assumption that the physical world is built from point-like particles and has replaced it with a vision of vibrating strings and higher-dimensional membranes. It has raised the prospect that our universe is just one among an enormous number of possibilities, and that the constants of nature are not unique, but contingent. These ideas represent a philosophical shift as significant as the Copernican revolution or the advent of quantum mechanics. Even if string theory is eventually superseded by a different framework, its philosophical legacy will endure. It has taught us to question our most deeply held assumptions about space, time, matter, and the structure of physical law. It has expanded the boundaries of what we consider to be thinkable and has reminded us that the universe is under no obligation to conform to our expectations. The quest for unification has never felt closer to complete than with string theory. Since the time of James Clerk Maxwell, who unified electricity and magnetism in the 19th century, physicists have pursued the dream of describing all the forces of nature within a single theoretical framework. The 20th century saw the unification of electromagnetism with the weak nuclear force into the electroweak theory, and the development of the Standard Model, which encompasses 3 of the 4 known forces. But gravity, described by Einstein's general relativity, stubbornly resisted incorporation into the quantum framework. String theory is the first approach to make genuine progress on this final step. It naturally includes the graviton among its vibrational modes. It provides a consistent quantum treatment of gravity, and it incorporates all the forces and particles of the Standard Model within a single mathematical structure. While the full realization of this unification remains incomplete, the framework is richer, more coherent, and more promising than anything that has come before. The quest for unification is one of the oldest and noblest projects in the history of human thought, and string theory represents the closest we have ever come to its completion. Whether proven or not, string theory has given us a new imagination of reality. String theory has offered humanity a vision of the universe that is breathtakingly ambitious and startlingly beautiful. It imagines a cosmos in which every particle is a vibrating string, every force is a consequence of geometry, and every dimension is a window onto deeper structure. It envisions our universe as a membrane floating in a vast higher dimensional space, surrounded by an infinite landscape of possible worlds. It tells us that the deepest truths of nature may be holographic, that space-time may be woven from quantum entanglement, and that the distinction between gravity and quantum mechanics may dissolve at the most fundamental level. These ideas have not yet been confirmed by experiment, and they may never be, but they have permanently expanded the human imagination, opening our minds to possibilities that were previously inconceivable. String theory has shown that the universe may be richer, stranger, and more interconnected than we ever dreamed. Whatever the future holds, this new imagination of reality is a gift that string theory has already given to the world. a quiet, enduring contribution to the long story of human curiosity about the nature of existence. And now, the quiet wonders of string theory begin to gently fade into the stillness of the night. You have wandered through over 100 peaceful truths about the hidden fabric of reality, from tiny vibrating strings at the Planck scale to vast brains drifting in higher dimensions, from the accidental discovery in the 1960s to the revolutionary dualities of the 1990s, from supersymmetric partners yet to be found to the holographic principle that rewrote our understanding of black holes. You have explored how strings may give rise to every particle and force, how hidden dimensions may shape the laws of physics, and how the mathematics of vibrations could explain the diversity of the cosmos. You have learned that beneath the familiar world of atoms and light, there may lie an invisible symphony, strings humming in silence, weaving reality with their hidden music. You are connected to this story more deeply than you may realize. Right now, as you listen, the atoms of your body may contain vibrating strings at their core. The forces that hold you together, the light that reaches your eyes, the very fabric of space around you may all emerge from the quiet resonance of strings too small to ever see. If your eyes feel heavy now, let them close. Let the rhythm of your breath become steady, like the gentle hum of a string vibrating in hidden dimensions, like the quiet pulse of reality weaving itself in silence. Tonight, as you rest, string theory continues its quiet work in the minds of physicists around the world. It waits patiently for experiments that may one day confirm its predictions. It inspires new generations to explore the deepest questions of existence. It offers a vision of unity that connects every corner of physics. You are a small, warm presence within this vast theoretical landscape, peacefully resting among the possibilities. Sleep well, sweet dreams, and may you carry with you the quiet knowledge that reality may be stranger and more beautiful than we ever imagined. That beneath the surface of everything we see, tiny strings may be humming, vibrating in patterns too small and too perfect for us to glimpse, weaving the universe into being. Thank you for joining me on this journey through the elegant depths of string theory. If you enjoyed this video, please subscribe to Drowsy Discovery for more soothing explorations of the mysteries that shape our universe. There are more wonders waiting, more secrets hidden in dimensions beyond our reach and in the mathematics of vibrating strings, more gentle truths to drift through on quiet evenings. Rest well, and may the hidden music of the cosmos keep you company through the night. This has been Drowsy Discovery. Good night.